What does it mean to say that matter is the ground of all things? If you listen closely to the long arc of Western thought about what things are made of, you hear a conversation that begins with scratchings in clay and water and winds toward a vast, unquiet field of forces and relations. This segment invites you into that conversation, not as a survey map with neat labels, but as a listening narrative. It follows a thread from the earliest thinkers who looked at the world and proposed that the secret of things lay in a single, simple principle, to later accents that shifted the ground from substance to structure, from static stuff to dynamic relations, and finally to fields, interactions, and networks that carry meaning beyond any one chunk of matter. It is a story about change and continuity, about why change looks continuous even when it seems to break out into difference, and about how the very idea of what something is can be reinterpreted as how it relates to something else. We begin with the very old, almost instinctive questions about the stuff of which the world is made. The story is not a single thread, but a braided set of intuitions that wrestle with a particular problem. If you taste the world, do you find a substance or a system of relationships? And if you claim it is a substance, what kind of substance is it? Water, air, earth, fire? Something else. The earliest presences in this inquiry come from the Milesian school, Thales of Miletus and Anaximander. And Anaximenes each proposed a single principle that could explain the multiplicity of things. Thales is often read as the first to identify the underlying principle as water. The canonical phrasing from traditional sources is blunt and powerful. Water is the principle of all things. It is not merely that water is found in many forms, rather. Water, in some sense, grounds the very becoming of everything else. In the ancient telling, this is less a scientific claim and more a metaphysical posture. The world is intelligible because a single, accessible material source animates it. To Thales, then, the world is not a mosaic of distinct substances so much as a field in which one primary medium manifests in many ways. Anaximander, in turn, pushes the question of principle beyond the visible toward the indefinite. The indefinite, or apeiron, is the source from which all things arise and to which they return. The ancient commentators give us a compact pairing. From the boundless come the boundless manifestations, from the indefinite, the finite and the diverse. The result is a framework where the world's variety does not demand an endless supply of discrete substances, but rather a single, generative principle that remains behind change while change itself seems to come into being. The language is almost poetic, the indefinite as source, the forms as appearances, yet the central claim is a form of unity that precedes appearances. Anaximenes, the third figure, offers a further refinement. If water anchors Thales' account at one end and the apeiron haunts Anaximander's, Anaximenes proposes air as the principle of all things. Air condenses into wind and cloud, it compresses into water and earth, it becomes the breath of life and the storm that shapes landscapes. The argument is straightforward, almost persuasive in its simplicity. When you thin air out, you get fire. When you thicken it, you get earth. In between lies the continuous chain that binds all forms. The intuitive power of this account lies in its economy. It does not require a multiplicity of substances to explain change. It demands only one active medium that can assume many states. In the mouth of Anaximenes, matter is a spectrum of densities, a continuous field of potentialities rather than a set of discrete, inviolable stuff. If we listen to these early voices with a careful ear, we hear two stubborn questions pressing in the background. First, is there a fixed, persistent stuff that endures across transformations, or is persistence itself a function of relational structure? And second, how does change occur without violating the sense that there is something real and stable beneath appearances? The Milesian trio offers a pragmatic answer. Change is the result of transformations of a single underlying medium. The world keeps its coherence because there is a single principle that can endlessly rearrange itself to produce the manifold we encounter. The problem of change, in their hands, is not a paradox of a universe falling apart, but a drama of transformation within a single, intelligible medium. But ancient material thinking was not content to stop with the Milesians. A century or so after these early figures, the dialogue moves to atomism, which returns us to the problem of substance with a new twist. Democritus and his partner Leucippus take a different route. If water or air can be thought of as the principle of all things, what if the world is built out of something utterly small and indivisible, something that underwrites all difference? The pair argue for atomism. Everything is composed of tiny, indivisible bodies, atoms moving in the void. The void, far from being nothing, is the space in which atoms can move. It is the necessary complement to the atoms themselves. Nothing exists except atoms and the void. They insist this is a radical claim. There are no essential forms or primary substances beyond the atomic arrangements. All difference, all qualities we perceive, color, hardness, sweetness are features of how atoms arrange themselves and interact. The contribution of atomism is both metaphysical and epistemic. Metaphysically, it introduces a primitive ontology. Matter consists of discrete, particulate units. Epistemically, it makes the continuity of change a matter of moving from one arrangement of atoms to another, with the caveat that the underlying substances are invisible and the laws of interaction are often hidden from casual observation. The famous statements attributed to Democritus echo the skeptical but exhilarating spirit of this view. Nothing exists except atoms and the void, everything else is opinion. Leucippus is sometimes heard as the precursor who added the crucial maxim, "From nothing, nothing comes." The intuition here is that change is not a matter of matter changing its form by some mysterious internal principle, but a matter of the arrangement and motion of underlying, invisible building blocks. If you hold atomism up to the light, you can ascribe to it a powerful explanatory force. It provides a straightforward story of how many things can emerge from few simple elements and how continuity is preserved not by a stubborn substance, but by the consistency of the atom's behavior and the void's permissive presence. Yet to many ancient readers and to many modern readers alike, atomism raises a stubborn question. What are the atoms like? What are their properties? How do we know about something that is essentially invisible? For the atomists, the answer lies in a combination of reasoning and experience. The idea that matter must be ultimately small enough to fit a mechanical story about contact, impact, and motion, and that the variety we see is a dance of countless indistinguishable pieces moving according to simple rules. Enter Aristotle, whose philosophy stands as a counterweight to the atomistic instinct and who imposes a different grammar on the problem of matter. Where the atomists locate substance in identifiable bits, Aristotle locates substance in a more relational, teleological network. His central move is to propose hylomorphism. Every physical thing is a compound of matter, hyl, and form, morphe. Matter supplies potentiality, form provides actuality. The form, the intrinsic organizing principle, gives the thing its determinate identity, while matter supplies the raw material that the form can actualize. This is not merely a quaint fusion of two ideas. It is a robust attempt to explain why things persist as the same things even when their appearances change, and how new organisms and artifacts come to be while they still have a recognizable identity. Aristotle's insistence that form matters as much as matter has two important consequences. First, it grounds a continuity of identity in the midst of change. Change is not the annihilation of substance, but the actualization of potentiality by form. When a seed becomes a tree, the tree is not simply the sum of its parts becoming something new. Its form organizes the matter into a specialized, persisting being. Second, it emphasizes purpose or end, teleology, as part of nature's logic. The form not only organizes matter but tends toward a final cause, an endpoint or function toward which natural processes seem to move. This is a real departure from the strictly quantitative, mechanism-focused vision of matter, and it foreshadows centuries of debate about whether nature's direction is purely mechanical or somehow teleological in a non-mystical sense. In this sense, Aristotle's view offers a sophisticated reply to the atomists' reductionism. The form can be seen as the principle that orders the atomic mosaic into stable substances and meaningful wholes, yet the tension between form and matter remains. If the form is what makes a thing what it is, then does matter have any reality independent of form? And if the form is the source of actuality, how does one square that with the subatomic, mechanistic program that would later become the heart of the scientific revolution? Aristotle's account does not yield a straightforward atoms and void ontology. Instead, it provides a framework in which matter and form are inseparable partners in the making of substances, in which change is intelligible as actualization of potential within a structured whole. The medieval period, in turn, confronts and harmonizes these strands in a broader Christian philosophical tapestry. If Aristotle's hylomorphism offers a robust ontology for natural things, Christian thinkers conceive of form and matter not merely as natural principles, but as echoes of divine order. The medieval synthesis does not abandon the ancient concern with substance and change. Rather, it treats form and matter as complementary aspects of a unified reality shaped by God's rational plan. This synthesis helps explain why matter can be both a substrate capable of receiving form and a participant in a teleological drama in which ends and purposes align with a cosmic order. The medievals often translate the Aristotelian vocabulary into theological terms. Form is a kind of structuring principle that endows matter with unity and purpose. Matter as the substratum that receives the form and makes that unity possible. As this medieval synthesis matures, another revolutionary claim begins to organize the mind. The 17th century brings a radical turn toward mechanism and mathematics, and into this blend steps René Descartes. Descartes, with his famous split between mind and body, offers a radically new metaphysical picture. Two kinds of substances, the res cogitans, the thinking thing, and res extensa, the extended thing. Matter, in his account, is extension. It has size, shape, and motion, but it is inert apart from the laws of mechanics that govern it. The world becomes a vast machine, with matter as the clockwork substrate. To speak of matter in Descartes' vocabulary is to speak of extension, bulk, and figure, and to explain its changes by the mechanical arrangements of parts in motion. The body, as a machine, is subject to motion, impact, and force in a way that can be understood through geometry and arithmetic. Far from any need to appeal to form or teleology in the organic sense, Descartes' mechanical philosophy is not a minor revision. It is a revolution in how to talk about matter. If the world can be understood as a giant clockwork of extended substances interacting through contact and motion, then you have a new scaffold for physics, one that makes the intelligibility of nature hinge on geometry, speed, and the contact of bodies. But this shift also generates tensions. The Cartesian move risks leaving behind the Aristotelian notions of form and purpose, and with them a sense of continuity that biological and natural kinds had previously enjoyed. The challenge becomes clear. Can a purely mechanical account do full justice to the diversity of natural phenomena, especially those that seem to require the idea of form or end? The question will echo through centuries as scientists and philosophers test the limits and aspirations of the mechanical picture. The 17th century does not only beget Descartes, it also invokes Galileo and Newton. Galileo's famous claim that the book of nature is written in the language of mathematics provides a powerful intellectual engine for the new science. The claim is not merely that mathematics is useful, but that it is the language through which the natural order reveals its structure. The world's laws, if properly read, should be expressible in mathematical equations, and the phenomena of motion, light, and matter can be traced through these equations with clarity and predictive power. Galileo's stance intensifies the mechanistic project. If matter moves according to universal laws, and if these laws can be captured by mathematics, then the old questions about form, substance, and the essence of matter recede before the force of quantitative law. In a sense, the older debates about whether matter is something substantial or a network of forces are reframed as debates about which mathematics best captures nature's order. But Newton arrives with a different kind of authority, one that blends the mechanical impulse with a new sense of explanation that refuses to be satisfied by pure speculative hypotheses. Newton's corpuscular conception of light is a landmark moment in the story of matter. He proposes, in a spirit of rational inquiry, that light might be composed of corpuscles that propagate through space. Much like particles in a fluid, the phrase hypothetically deployed, later to be called a corpuscular theory of light, gives a concrete, testable picture of how light interacts with matter, refracts, and reflects. His refusal to cede to unfounded conjecture is captured in his famous line, "Hypotheses non fingo, I do not feign hypotheses." It is an invitation to an empiricist discipline. Let us ground our explanations in observable phenomena and the measurable consequences they produce, rather than in speculative metaphysical commitments. Newton's approach does not reject the idea that matter might be a complex, structured thing. It simply demands that we treat such complexity with mathematical clarity and empirical discipline. Yet even as Newton's physics opens new horizons, the philosophical underpinnings begin to shift in unexpected directions. The mechanical philosophy, with its insistence on extension and motion, runs into new kinds of challenges as science advances. By the late 18th and 19th centuries, materialist currents begin to argue that matter, at its core, is nothing more than a system of particles in motion, governed by laws of physics and chemistry. Materialism, in this sense, takes a radical turn. It claims that the entire cosmos, including life, mind, and society, can ultimately be explained in terms of the same material substratum. The appeal is obvious: a single, coherent, testable framework can account for a broad spectrum of phenomena without recourse to mysterious or non-physical explanations. But this move also raises questions about the limits of a purely mechanical story. If all of reality is reducible to particles colliding and fields mediating forces, what becomes of qualities, meanings, and experiences that seem distinct from such interactions? What happens to the qualitative richness of wholes and to the teleology that Aristotle once thought indispensable? In par with these debates, a crucial shift begins to take shape. The rise of field thinking, pioneered in the 19th century by a pair of brilliant minds, Michael Faraday and James Clerk Maxwell. Faraday, in particular, reframes the problem by moving away from a world of little bodies and their collisions toward a world of lines of force and invisible interactions that propagate through space. He uses a language of fields to describe how one charge can influence another without contact, how electricity and magnetism become connected through a universal medium of influence. The field, in Faraday's hands, is not merely a convenient mathematical tool, it is a real entity with causal powers. The image of the field helps dissolve some of the stubborn problems of action at a distance in the older mechanistic accounts and points toward a more relational, dynamic picture of how matter engages with the world. Maxwell then takes Faraday's intuition and turns it into a coherent theoretical edifice. He codifies the electromagnetic field with a set of elegant equations that describe how electric and magnetic fields propagate, interact, and give rise to light as a wave phenomenon. Maxwell's equations reveal that light itself is a manifestation of the field, and that the very nature of matter and energy is intertwined with the structure and dynamics of fields. The field approach signals a shift from a world of substances to a world of relations, a universe in which forces are not simply properties of particles, but patterns of interaction that stretch through space. This is not a rejection of matter, it is a reconfiguration of what counts as the fundamental constituent of reality, in the language of the time. Fields are not mere add-ons, they are new ontological commitments that redefine how we think about causation, interaction, and the potentiality of matter. If we pause here and listen to the echoes of the conversation, we hear a chorus of voices offering different answers to the same essential questions. On one side, atomism offered a robust, discrete ontology that could explain the diversity of materials and the emergence of new substances through recombination of tiny parts. On another side, Aristotle's hylomorphism insisted that form matters, and that the world's intelligibility depended on the unity of matter and form and the teleological sense of natural processes. The medieval synthesis tried to harmonize these strands within a theological frame. Then, the 17th century thrust toward mechanism and mathematics reoriented the problem toward extension, motion, and quantitative law. The 19th century field thinking, in turn, redirected attention to relational structures and the medium through which interactions propagate. The debate is not simply about whether matter exists in a certain form, it is about what counts as the most persuasive, causal, and explanatory core of reality at this point. It can be helpful to bring in a few concrete examples that illuminate how these ideas play along in the real world. The first concerns the vacuum question and the Torricellian experiment of 1643. Torricelli fills a glass tube with mercury and in the process creates a partial vacuum above the mercury column. The result is a barometer that demonstrates something startling. Nature does not require a full, continuous medium to fill the space. A void can exist, at least momentarily, within a physical arrangement. The idea that nature abhors a void, an ancient intuition that had given physics a ready explanation for why substances filled space, begins to be challenged. The vacuum becomes not just a counterexample to a simple material picture, but a motivation for considering more subtle accounts of pressure, motion, and interaction. This experiment does not merely prove the existence of a vacuum, it invites a rethinking of what counts as a constituent element of nature, if space can be empty. And if measurement reveals a structure of pressure that acts across space, then the question shifts. Is the fundamental reality something that resides in a block of matter? Or is it a pattern of fields that can act where no matter is present in the ordinary sense? Second, consider Newton's corpuscular theory of light as a parallel to material explanations. The idea that light might be composed of tiny particles challenges the field picture that would later dominate. It shows that early scientific imagination often flows between the extremes of substance and interaction, between a world of little bodies and a world of lines and influences. The corpuscular hypothesis is attractive because it offers a straightforward mechanical account. Light travels as particles that collide, reflect, refract, and interfere in ways that can be described arithmetically. But wave phenomena, such as interference and diffraction, reveal the limits of a purely particulate picture and lay the groundwork for future field theories. The debate between particle and wave, the dual nature of light, becomes a broader allegory for how scientists conceive matter and its interactions. Is there a single, underlying substance? Or is the essence of physical phenomena the pattern of relationships and energies that animate space? A third example arises with Faraday and Maxwell's field concept. Faraday's insistence that lines of force carry physical significance reframes what counts as causal agents. The field is not merely a convenient mathematical device but a real, physical entity in which energy is stored and transferred. Maxwell's equations show how these fields obey laws, how they propagate as waves, and how their interactions with matter yield the familiar phenomena of electricity, magnetism, and light in this sense. The modern understanding of matter begins to loosen its attachment to discrete particles as the sole carriers of influence. The field suggests a more radical possibility. The fundamental reality might be a network of interactions, with matter as a particular manifestation within that network rather than the primacy of the hard, indivisible particles themselves. The shift is not that substance disappears, but that its status is reinterpreted. A piece of matter is now something that has properties relative to fields, to potentials, to energies. A fourth and particularly important thread concerns the 19th century currents of materialism and their critics. Materialist philosophers, including certain strands of British and German thought, argue that the whole of reality can be explained by the interactions and arrangements of matter. Mind, consciousness, social life, culture, these are all, in some sense, reducible to matter in motion. The strength of this claim lies in its unifying ambition, a single framework that can, in principle, explain every phenomenon by mechanical or physical forces, but the counterarguments are significant. Parmenides and Zeno challenge the very legitimacy of motion. To them, change is an appearance, and the sense of continuity may be illusory. Berkeley's immaterialism, with his famous esse est percipi, pushes back against the sufficiency of a purely external world in which matter is the sole protagonist. Kant, in a different key, suggests that there are limits to what we can know about the thing in itself, and that our knowledge is always filtered through the forms and categories of our own cognitive architecture. The 18th and 19th centuries do not settle these issues, they intensify them, forcing philosophers and scientists to consider whether the substance-centric picture is compatible with the evidential richness of experiments and with the success of theories that emphasize forces, fields, and structures. From these debates, a crucial pivot emerges, the emergence of field thinking as a serious ontological option. Faraday's bold move to describe electricity and magnetism in terms of fields, and Maxwell's mathematical consolidation of that idea, herald a new way of thinking about matter and its relations. If fields are real, if they carry energy and exert influence across space without requiring a continuous matter to fill every region, then the fundamental picture of reality shifts from a universe of discrete building blocks to a universe of relational structures. This shift does not erase the historical significance of atoms and molecules. Instead, it reframes them as particular configurations within a field, as excitations of a relational medium rather than as the ultimate stuff in itself. The field is a medium that allows for interaction, energy exchange, and codification of physical law in a form that respects locality and causality while transcending the old insistence on direct contact. The cross-cutting implication of this transition is that matter itself becomes a term that must be interpreted relative to the theory in which it sits. If you are a materialist who believes that substance is the ultimate anchor of reality, you might insist that matter remains the ground of all phenomena and that fields are only tools for describing how those substances move and exert force. If you are a field thinker, you might insist that the real entities are fields, never merely conditions in space that matter experiences, but the actual relational scaffolds that instantiate reality as dynamical structure. The philosophical debate then deepens into a question about realism versus instrumentalism. Are fields real elements of the world, with causal powers and ontological status independent of what we can measure? Or are they instruments for organizing our experiences and computations, useful for predicting outcomes but not necessarily reflecting an underlying substance? These are not merely academic concerns. They shape how science interprets data, how experiments are designed, and how we conceptualize the relationship between mind and world. To illuminate these questions further, let us consider two more anchors in the historical story: the turn toward realism and the challenge from idealism and epistemology. The realist position asks, do the objects and fields of our theories literally exist in the world independent of us? Or do they simply structure our experience? The instrumentalist counterpoint asks, if a theory works well for predicting phenomena, does it have to mirror the world as it really is? Independently of human concepts, these cross-cutting issues arise in many contexts but are especially vivid in the early modern era, where the shift from substance to field, the rise of mathematics, and the crackle of experimental data converge into a new scientific ethos. They echo forward into the 20th century and beyond, influencing debates about the status of the unobservable, the role of observation, and the nature of scientific explanation. If we step back and inhabit the long view, we see the origins of field thinking not as a sudden rupture, but as a response to persistent difficulties that the older accounts could not fully address. The vacuum question, for instance, is not simply a practical curiosity. It is a philosophical invitation to re-examine what counts as a fundamental constituent of nature. If space can hold something void and still be part of a physical description, if the behavior of light and matter suggests a common descriptive language, if the energy content of fields can be conserved and transformed across space, then the ontological stakes shift. The real things may not be the smallest bricks of matter, but the relations that bind them into stable, findable patterns. The shift toward fields resonates with ancient intuitions about interconnection, the sense that reality is a coherent whole rather than a mere pile of discrete bits. As we reflect on the arc from Thales to Faraday and Maxwell, a few essential themes emerge that can guide further study in future sections. First, the problem of change and continuity has been a constant in this history. How can we reconcile the stable sense of things with the flux of experience? The Aristotelian solution, form active in matter, potency becoming actuality, offers one way to think about this. The atomists offer another. Continuity arises from the arrangement and motion of a fixed set of building blocks, even as appearances shift dramatically. The medieval synthesis preserves continuity through a teleological narrative that situates natural processes within a divine order. The mechanists reframe continuity in terms of deterministic dynamics and mathematical law, while field thinkers reframe it as a network of relational influences extending through space. Second, the debate about substance versus relation is not merely metaphysical. It is deeply tied to how we model and interpret the world. In practice, scientists often inhabit a space between these extremes. There are times when treating matter as a substance works best. There are times when treating matter as a network of forces or fields yields new predictions and a more accurate description of phenomena. Cross-referencing thinkers across the centuries helps to illuminate why those choices work in different contexts and how the right kind of account can evolve from a particular scientific problem. Third, we should recognize the ongoing relevance of these debates for modern science. The push toward field thinking does not erase the older achievements of atomism or hylomorphism. Instead, it reframes them as different layers of understanding. The field view has become central in modern physics with quantum field theory, where particles are seen as excitations of fields, and even the concept of a classical substance appears subordinate to field and interaction. Yet the older questions about form, purpose, and teleology still arise in philosophy of biology and philosophy of mind, where one asks whether organizational principles and forms are properties of matter itself or of the patterns and relations that matter sustains. The cross-reference with the philosophy of science debates realism versus instrumentalism, substance versus field ontology, and the shift from substance to relational thinking remains essential for a deeper understanding of why science has the shape it does today. To bring this narrative into sharper relief, here are a few guiding threads you can carry into the next sections and later videos. 1. Keep in mind the problem of change as a central preoccupation. The ancient insistence on a single principle, water, aperin, or air, frames change as a transformation within a primary medium. The atomists refuse to deny change but insist it occurs through discrete, invisible bits in motion through the void. Aristotle wants to preserve continuity by showing how form actualizes potential in matter. The medieval thinkers want unity within a divine order. Descartes wants a clean, mechanical explanation that can be subjected to geometric and mathematical analysis. Galileo and Newton want the language of mathematics to illuminate natural law. The 19th century asks whether atoms alone suffice or whether fields must be acknowledged as the real carriers of causation. The field revolution, as you will see in upcoming segments, ventures into an ontology in which relations become the primary dancers on the stage of nature. Fourth, this history is also a repository of human astonishment. We are not simply cataloging claims about matter. We are listening to the way human beings have imagined the hidden structures that produce what we can see, touch, and measure. The vacuum is a riddle that invites us to revise what counts as something and what counts as nothing. Light's dual character, whether as particles or waves, presents not just a technical problem but a philosophical puzzle at the heart of what we consider physical reality. Fields, with their geometry and their energy, invite a broader sense of causality. a causality that operates through spaces and patterns rather than through direct contact alone. These are not merely technical issues. They shape how cultures conceive of reality, how they frame education, how they imagine the future of science, and how they place human beings in relation to the cosmos. Now, to weave primary source voices into this living narrative, consider the core lines that scholars often hold up as milestones. Thales is said to have claimed that water is the principle of all things. The point is not simply the water itself, but the idea of a unifying medium underlying multiplicity. Anaximander speaks of the apeiron, the indefinite or boundless, as the source of all that exists and changes. This is a move toward a generic principle rather than a specific substance. Anaximenes takes the next step by identifying air as the underlying principle, presenting a spectrum of states from rarefied air to thick air as the engine of transformation. Democritus and Leucippus crystallize a radical atomism. Nothing exists except atoms in the void. The claim is stark and audacious. The world is built from the invisible arrangement of tiny, indivisible bits, and everything else is a result of their shapes, motions, and the empty space in which they roam. Aristotle then enters with a different cadence. The matter is not merely a raw substrate, it is a material in which form actualizes potential. And this process of actuality is what yields the diverse realities we encounter. The famous Aristotelian aphorism that nature does nothing in vain permeates the discipline. Hylomorphism integrates form and matter into a single explanatory framework, an insistence that the what of a thing and the how of its coming to be cannot be fully separated. In the medieval period, the synthesis matures into a robust, practical philosophy in which form and matter cooperate within God's order to explain natural phenomena and human knowledge. Descartes introduces a crisp dualism that emphasizes the extension of matter and the thinking mind as two separate kinds of substances, with the body as a mechanical entity. The modern science that follows is shaped by this dichotomy, explain phenomena through the geometry of bodies in motion and through the laws that regulate their interaction. Galileo cements a crucial methodological claim. The book of nature is written in the language of mathematics. The claim is not a metaphysical assertion alone. It is a methodological program, explanation through precise, quantitative relationships. Newton sharpens the program with a robust empiricism, refusing to propose hypotheses that cannot be shaped by observation. The corpuscular approach to light demonstrates that a mechanical explanation can extend far beyond matter itself to the very way we perceive phenomena such as color, refraction, and momentum. In the 19th century, the field becomes a central model for thinking about matter and its interactions. Faraday's insight, writing about lines of force in the field as a real medium, offers a way to conceive causation without recourse to direct contact alone. Maxwell's equations then crystallize the field into a coherent, predictive framework that unifies electricity, magnetism, and optics into a single theoretical spectrum. The field picture helps to account for phenomena that resist purely particulate explanations, and it opens up new ways of understanding the nature of reality. As Einstein's later insights reveal, field thinking can be extended even more radically to show how mass, matter, and energy interpenetrate in mass-energy equivalence, a concept that reshapes our sense of what matter is at the deepest level. Throughout this journey, remember two recurring themes that will echo in future segments as well. One is the tension between realism and instrumentalism. Are our theories about matter truly describing mind-independent structure, or are they instruments that help us predict, manipulate, and control the world? The other is the question of how much of our conceptual framework is a product of history, the particular problems, experiments, and mathematical tools of the time versus an inexhaustible description of the world itself. These are not merely academic questions. They shape how new theories are evaluated, how scientific revolutions happen, and how we interpret data in light of old and new ontologies. As we move toward later chapters and future sections, we will continue to test these ideas against the ongoing work on substance, form, and field. We will examine how the empirical successes of field theories negotiate with the intuitive appeal of substance, and how modern physics increasingly blurs the line between the two. We will also bring in cross-references to the philosophy of science debates about realism and instrumentalism. And we will explicitly connect to later segments on the shift from a world of little bodies to a network of forces. The aim is not to settle the matter once and for all, but to illuminate how this question has shaped, and continues to shape, our most fundamental intuitions about what matter is, what it does, and how we come to know it. To close this segment, I want to offer a handful of resonant lines that crystallize the mood of this historical arc, not as definitive statements but as touchstones for reflection. Thales, you might say, invites us to begin with a solvent principle, a unifying medium that makes sense of difference. Anaximander asks us to consider the indefinite, the source that remains beyond the deficit of every particular thing. Anaximenes asks us to attend to a single principle again, but this time in a state that can account for a continuum from air to water to fire. Democritus and Leucippus push the exploration into a different plane, the plane of the void and atoms in perpetual motion. Aristotle offers a different grammar, form and matter. Potentiality and actuality, that accounts for the becoming of substances within a structured natural order. Descartes fires a rebellion against the older scholastic and Aristotelian frameworks by making extension the primary property of body and by insisting that the universe is a machine. Galileo and Newton insist that mathematics is the language through which nature narrates its laws. Faraday and Maxwell invite us to listen to fields as real carriers of causation, not merely as mathematical abstractions. And the 19th century currents of materialism remind us that powerfully simple ideas can drive science forward, even as later developments demand more intricate and relational pictures. In the next segment, we will dive deeper into the two counterpoints that have persisted across this history, the problem of illusion in change and the challenge to purely mechanical explanations that appear to oversimplify the richness of natural phenomena. We will explore Parmenides' diagnosis of the illusion of change and Zeno's paradoxes in more detail, showing how their critiques still haunt both metaphysical and scientific theories of matter. We will also turn toward Berkeley and Kant to examine the epistemic and perceptual constraints that complicate any straightforward appeal to substances. Then we will pivot back toward the 19th century and the rise of field thinking, culminating in an exploration of Einstein's synthesis of matter and energy, where the old dichotomies between substance and field finally find a new, unified horizon. As you listen to this, the aim is not to accrue a catalog of names and quotes, but to cultivate a sense of how the problem of matter has always been a problem of vision, how we see what counts as the fundament of reality, how we listen for causation, and how we judge the plausibility and fruitfulness of competing pictures. The history of matter from Thales to field thinking is a history of the imagination learning to adapt its grammar to the stubborn facts of experience, a history of how the human mind translates the stubborn fact of persistence and the bright fact of change into stories that can be reasoned, tested, and taught. And as we proceed, we will keep returning to the central tension, substance versus relation, and we will watch as modern physics, with its fields and its quanta, reframes the ancient questions for a new era. The conversation continues, and the questions endure. What at base is matter? How does it endure? What gives it its form or its field? And how do we, as knowers, listen to the universe to hear what these answers might be trying to tell us about the nature of reality itself? Think of a rock sitting in a quiet stream, or a crystal lattice perched in a geode. Most of us would say plainly that there is matter there, a thing that weighs something, occupies space, resists a push, and carries a certain color or texture. But under a philosophical microscope, that plain intuition becomes a battleground. What exactly is the rock? Is it a persistent substance, an enduring stuff that holds steady through change? Or is it a bundle of relations and qualities, a pattern of interactions that only appears to be anchored by some deeper substrate? Or perhaps the rock is best understood as the field of forces and potentials that surround and organize it, a framework within which particles and energies dance. And how should we think about the modern relatives of matter, mass, charge, energy, and the space-time that houses them, and what do those notions demand of any ultimate account of what exists? In this segment, we embark on a long, careful walk through the metaphysical landscape of matter. We start with the oldest accents of the debate, the idea that substance, the basic, persistent stuff of reality, had to ground the things we see. We then listen to the rival voice that asks, could everything be grounded in relations, in how things stand to one another, rather than in a stubborn substratum? From there we rise into the field-centric turn that modern science invites, tracing how Faraday's lines of force, Maxwell's equations, and Einstein's spacetime reshaped what counts as real. We press forward to contemporary positions, Spinoza's monism as a radical unification, and emergentism as a hedge against both pure substance and pure relation, and we weigh their strengths and their arguments, along with robust counterarguments that have kept the debate alive for centuries. As always, we will anchor the conversation in concrete examples and vivid historical anecdotes. Because metaphysical theories do not float in a vacuum, a rock is not merely a rock in a lab sense, it becomes a test case for how best to understand what is real. A magnetic field is not a mere abstraction. It plays a real causal role in shaping the way matter behaves. A quantum field, if taken seriously, may be the ground of particles themselves. And by gazing at these illustrations, we glimpse how different thinkers would answer a simple, stubborn question: what must matter be? If we want to understand the structure of the world without reducing it to purely numerical correlations or to a grimly unhelpful alphabet of appearances, let us begin with the origins of the debate. The oldest continuous thread runs through the history of philosophy as a preoccupation with solid, changeless support. In the ancient and medieval worlds, the question was more often framed in terms of substance, as something that remains the same through change, something that bears the properties we observe without itself changing. Aristotle, for example, is foundational here. But in a distinctive way, he does not treat matter as the raw stuff that simply persists while properties come and go. Instead, he introduces a more nuanced account called hylomorphism, a marriage of form and matter. In Aristotle's view, every concrete thing is constituted by matter, hyl, and form, morph. Matter on its own is potentiality, unformed, undetermined, a kind of raw material that could become any of a range of forms. Form, by contrast, is actuality, the organizational principle, the pattern, the structure that actualizes the potential of matter, the statue, the bronze, the shape of the teapot, and even the substance of a person's life. These are instances of form actualizing matter. If we translate Aristotle into modern language, we could say that matter supplies the substrate, but form supplies the laws of organization. The rock in the stream is not simply the same lump of stuff forever. It becomes the rock because of the arrangements that hold its molecules, the crystalline lattice if it's a mineral, the bond structures, the symmetries, the temperature and pressure conditions that guide how it's put together. Yet for Aristotle, form is not merely ornamentation, it is real causal principle. It makes a thing what it is, the rock's solidity, its hardness, its color, and its set of causal powers to resist deformation. These are not properties floating free in space. They are instantiated because matter has taken a particular form. Descartes enters the scene a bit later with a shift in emphasis, one that simultaneously fractures and reconfigures the older unity of form and matter. For Descartes, the fundamental division in nature is between two distinct substances, the res cogitans, or the thinking thing, and the res extensa, extended matter. The body, for Descartes, is a thing that occupies space, has extension, and follows the laws of mechanics in a way that is profoundly different from the mind, which exists outside of spatial extension and is governed by rational thoughts and ideas. He famously separates the two as two kinds of substances with two kinds of attributes. The mind has the attribute of thought, matter has the attribute of extension. In this framework, substance is what persists through change. But the persistent thing must be of a kind that can be described in its own right by certain essential attributes. The celebrated phrase res extensa captures Descartes' commitment to treating matter as extended substance, a thing whose essence is extension. He thought that by focusing on extension as the primary attribute of body, we gain access to a mechanistic picture of the physical world. In his famous pronouncements, the body, what we ordinarily call matter, becomes for him a thing that can be measured, weighed, moved, and arranged. This is not a trivial shift. It splits up the nature of reality into two kinds of substances with distinct causal profiles, and it will push thinkers toward a variety of responses to the ground of reality. Is there a single, more fundamental substance that underwrites both mind and matter? Should we ground everything in the interactions of fields and forces, rather than in materials that persist through time as things? From Descartes and Aristotle, we move toward a more radical reimagining of what grounds physical reality, the rise of the field. The field is not merely a convenient bookkeeping device. It is a new kind of ontological commitment that seeks to explain how forces act at a distance, how things influence one another without touching, how energy and causation can be described as patterns that inhabit space. The field idea emerges through a long, careful accumulation of empirical successes in electromagnetism and later gravitation, culminating in the 19th century with Faraday and Maxwell. Here the rock becomes a test example. Is it a simple thing with intrinsic properties that endure through time? Or is it a region of space where forces and potentials produce a stable pattern of interactions? If the latter, then even a seemingly solitary rock might be better understood as part of a field configuration, a region in which magnetic influences, gravitational gradients, or other field lines exercise causal power. Faraday, with a gentleness of language that sometimes reads like poetry, is one of the earliest great advocates of the field as a real ontology. He does not merely talk about forces, he speaks of lines of force, something visible in experiments with electric and magnetic phenomena, something that can be drawn on paper but is meant to capture the real causal structure of the world. The image is not of things acting over distance by some hidden mechanism. The field is the real entity, the thing that organizes how charges will influence each other and how matter will respond to those influences. Maxwell, in translating Faraday's intuitive field picture into a precise mathematical framework, gives us a set of equations that describe how fields propagate, how they interact, how they carry energy and momentum, and how they influence the motion of bodies and particles. And as the 19th century closes, the field begins to look not merely like a convenient descriptive tool, but as a real, densely physical substrate of reality. There is wisdom and surely a certain elegance in the way field theory reframes our old questions. If a rock is a field configuration, perhaps the word rock is a misleading shorthand for a pattern of field values in a particular region of space. The rock's solidity, the fact that it resists fracture, that it has a given density, that it imposes inertia on a moving object, emerges from the stability and organization of the field around it. Even the mass of the rock, which in Newtonian terms is a property of the body, can be recast as a field property, something determined by the way the field stores and transmits energy and interacts with spacetime. In this move, matter becomes not a simple substance with intrinsic properties, but a node in a field network, whose behavior is a reflection of the field's dynamics. The shift from substance to field is not a mere change of vocabulary. It redefines what we take to be real causal agents. If fields are fundamental, then the basic ontological commitment is not to things that endure, but to the relational, structure-bearing patterns that fill the fabric of space. The field itself can be unseen and yet have tangible consequences. A magnetic field can guide the motion of charges, shaping what counts as a rock's magnetism. An electric field can influence how molecules bind or vibrate. Gravitational and spacetime curvature can guide orbital dynamics for planets and satellites. The field voice, which Faraday and Maxwell helped articulate, thus enters the story as a candidate for grounding reality more fundamentally than a mere bundle of material properties or a stubborn substratum. But the field turn also invites critique, among which two stand out as especially persistent. The first is the persistence problem for relational theories. If the fundamental ontology is a network of relations, things are defined by how they relate to other things, then what ensures that these relations themselves persist through time? Or that a stable object continues to exist as a unity rather than dissolving into a shifting mosaic of relations? In relational theories, the identity and persistence of objects can appear derivative, dependent on a structure beyond the object that we intend to explain. Without a robust sense of what grounds that persistence, the rock might seem to drift into a web of interrelations in which there is nothing to pin a definite, enduring thing to. The second major critique is a practical one: the apparent success of substance-based language in science. There is a long-standing sense in which everyday scientific discourse, talk of atoms, molecules, crystals, protons, still speaks in terms of substances. Even if the underlying formalism describes fields and interactions, scientists often reintroduce objects as useful foci for explanation, prediction, and manipulation. The language of substance sticks in the popular imagination, and many specialists grow comfortable with a hybrid picture in which fields are fundamental in theory, but substances remain indispensable in modeling experiments and tangible experience. The field ontology, even if compelling in principle, must account for the successful intuition and explanatory power of substance-based descriptions in laboratories and classrooms. A further layer of complexity arises when we consider not just classical fields but quantum fields, and more broadly, quantum theory's notorious insistence that the ground of reality might be neither substance nor field in the everyday sense, but a different kind of unity altogether. In quantum field theory, particles are excitations of underlying fields, and the properties that appear to define individual objects, mass, charge, spin, are manifestations of field states, while the field itself becomes the more fundamental scaffold. In this light, the rock ceases to be a stable chunk of matter with intrinsic properties and instead becomes a pattern of quantum field excitations that, under appropriate conditions, organizes into stable, robust phenomena recognizable as solids. The ontology that results is subtle and deeply satisfying to some, and perplexing to others, because it dissolves the old boundary between thing and field, and asks us to see reality as a spectrum of modalities in which matter, energy, and spacetime are incessantly braided, Let us deepen this discussion by turning to the philosophical portraits of a few guiding figures who illuminate the different sides of the matter question. We begin with Descartes, move to Aristotle, then move to the decisive turn of Spinoza, and loop forward to Kant and the English empiricists. Then we will press into the field era with Faraday and Maxwell, and finally enter the modern replacement of substance by field through Einsteinian spacetime and mass energy. Throughout, we will return to the same set of core questions. Must matter be a persistent substance? If not, can relations or fields ground reality in a more fundamental way? How do the ideas of mass, charge, and energy fit into these schemes? And what do these commitments imply for our understanding of the mind-matter relation as we tease apart appearances from noumena in later segments? Let us begin with Descartes, whose metaphysical project is built on a resolute dualism. In the Cartesian framework, the body is not identical with the mind. The body is a physical extended substance, a res extensa, whereas the mind is an immaterial, thinking substance, res cogitans. The body's essence is extension, the property by which it takes up space. He writes in effect that extension is what defines the material. The body is that which is extended in length, breadth, and depth. What does it mean for something to be extended? It means it has dimensions, it has shape, it occupies region in space. And precisely because the body is extended, it is subject to mechanical laws. It can be pushed, pulled, rotated, cooled, heated, broken. The mind, by contrast, is characterized by thought, perception, and conscious experience, not by extension. The mind and body seem to belong to two different species of substance, two distinct ontological kinds. This split elegantly explains certain empirical facts. Mental states do not seem to be spatially extended, physical states do. But it also raises questions about how the two interact. If the mind and body are different substances with different essential properties, how does a mental intention cause a bodily movement? How does a fender bender in the physical world give rise to a pain or a memory in the mind? Descartes' own solution hinges on a form of interactionism. The mind and body interact through the pineal gland, a region we might note that modern science does not take seriously as the seat of mind-body interaction. The more important point for our topic is not the biology of the pineal gland, but the way his system treats matter as a substance with a definable essence. Here extension, which carries causal powers within the mechanical framework. In Descartes' hands, substance persists because extension is a stable property of bodies, a property that survives changes in motion, shape, or state, and thereby preserves the identity of a body through time despite the flux of its particular configurations. Substance, in this sense, is the ground of persistence. It is what remains when we strip away a thing's changing appearances. Descartes thus anchors the discussion in a robust form of substance ontology, where matter is a discrete thing with a determinate essence, extension. It is a worldview in which the underlying unity of the world is not a field or a network of relations, but a zoo of substances, each with their own intrinsic properties and laws of motion. The world, from this vantage, is a congeries of individual things, each a substance whose persistence is secured by a principle of extension. The consequence is a natural science organized around the deduction of mechanical laws that govern the interactions of these discrete, substantive bodies. The method is mathematical, precise, and outward-looking. Observe how bodies move apart or together, what forces seem to act, and how the shapes and sizes of bodies relate to those forces. Moving a little further back in history, Aristotle's hylomorphism offers a contrasting template. For Aristotle, matter does not carry an intrinsic essence on its own in the way Cartesian substances do. Rather, matter is potentiality, the raw stuff that can be formed into any of several actualities by form's organizing principle. The many becomes the one through a process of actualization. A bronze statue is not merely a lump of bronze with innate properties. It is a compound of matter in the form of statueness. The matter supplies the resources. The form supplies the figure. In this sense, the rock's solidity, its crystalline structure, or its color are not attributes that matter has independently of a regulating form. They arise because form orders matter into a determinate kind of thing. The rock remains what it is because it has a particular form that actualizes the potential in the matter in a specific way. The Aristotelian position thus shifts the ground of grounding, not a persistent thing that endures, but a process in which matter is always and only what it is in virtue of form. And form is the principle that makes matter into something with definite, intelligible, causal structure. The form is not simply a mental label. It is a real principle that confers unity, limits, and law-like order upon matter. The rock, in this sense, is not an isolated thing in itself with intrinsic attributes. It is the outcome of a specific formal organizing principle in matter. The form defines the rock's identity, and the matter provides the substrate that actualizes that form. It would be a mistake to regard Aristotle as a primitive advocate of a vague essence that clings to matter. Instead, he offers a dynamic way to understand how the unity of a thing arises from the interplay of substrate and structure. These early accounts set the stage for later, subtler challenges to the primacy of substance. In the modern period, Baruch Spinoza offers a compelling and controversial alternative that both embraces unity and challenges the relativization of substance to subject-specific categories. Spinoza, in his mature system, is what we would call a monist of a very particular sort. For him, there is only one kind of substance, God or nature, a single substantive reality in which infinite attributes express God's expression. What looks like many substances in the world we experience, minds, bodies, forces, fields, are ultimately modes of a single underlying substance. The famous claim, Deus sive natura, is not merely a slogan, it encodes a rigorous metaphysical program. In Spinoza's ethics, the mind and the body are not two different substances or even two separate features of a dualistic substratum. They are two attributes of the same one substance. Seen from different angles, the mind is the idea of the body is the mode through which thoughts are expressed, and thought is the way in which the body is determined. To quote Spinoza in his own register, we might say that God or nature is one substance with infinite attributes of which humans can know only two, thought and extension. This is a stunning reconception of reality. If there is only one substance, then the apparent plurality of objects and forces in the world becomes a unity understood through the lens of how this single substance expresses itself in various attributes. The mind and the body are not, then, two separate things but two ways of thinking about the same thing. This is not merely a semantic trick. It is a claim that the underlying ground of reality cannot be exhaustively captured by the language of distinct, enduring substrata at all times. Instead, it calls for a form of ontological economy. The diversity of appearances is the result of the different modes through which the one substance manifests itself. Spinoza's monism prompts a deep question for our broad topic. If there is only one substance, what is the status of field-like or relational accounts? In a sense, Spinoza dissolves the problem by dissolving the problem space. There is no void in which relations or fields stand apart. Everything is within the same substance. And what we call a field or a mode is simply a way of describing a particular pattern of expression within that one substance. This reimagines ground not as a substratum or a field that exists independently of the objects it grounds, but as the very texture of God or nature's own being. Yet Spinoza remains a controversial figure precisely because the monist move can feel to many readers as an abstract metaphysical system that lacks the kind of crisp causal direction we expect from physical theories. If there is only one substance, how do we explain the causal efficacy of one thing over another, or the appearance of attraction and repulsion that we see in experiments? Spinoza's answer lies partly in his strict handling of God's nature as an impartial, necessary being, and in his claim that the order of nature flows from the necessity of that single substance's own nature. In practice, his system invites a reinterpretation of causation, not as the intervention of discrete substances upon one another, but as the necessary interplay of attributes within one overarching reality. The arrival of Kant's critical philosophy injects another powerful dimension into the matter problem. Kant does not deny the reality of the empirical world, to be sure, but he insists that our knowledge of it is constrained by the mind's own forms of intuition and categories of understanding. In his famous line, "Two things fill the mind with awe, the starry heavens above and the moral law within." This bracing statement signals a recognition that while appearances present themselves to us in the world of phenomena, there could be something beyond that, a noumenon or ding and sitch, that lies beyond the reach of any possible intuition. Kant asks us to distinguish between appearances, which are structured by space, time, and causal laws as our minds must impose them, and things as they are in themselves, which we cannot fully know. This is a crucial move for the matter question because it suggests that there may be a limit to how much we can claim about the substance of matter in itself. We may know matter as it appears to us under the forms of our own cognition, the way that extension, causality, and numerical relations structure experience. But what the thing in itself would be beyond such structure remains unknowable. Kant's position has a twofold effect on the debate. It preserves the real dependence of science on the human knower, and at the same time it introduces a caution about any strong claim that matter must be grounded in a single, timeless substrate that resources all causal power. He thus creates space for the possibility that the ground of reality, what is ultimately real in itself, may be beyond our direct access, while the world of appearances, including all the robust scientific theories we rely on, is the field in which we operate. In this sense, Kant does not deliver a final verdict on substance versus field. He rather reframes the problem as one that must account both for the settled success of empirical science and for the epistemic humility about what lies beyond appearances. The empiricist tradition in England adds another voice to the chorus. John Locke and later David Hume push the question into a different lane. Locke is often read as complicating the substance idea by insisting that we have no direct idea of substance itself. We perceive the objects, their sensible qualities, color, weight, shape, texture, but the substrate that supports those qualities, the substance, remains unknown to us in itself. In this sense, Locke's position is a cautious realism. Substances exist as a practical scaffolding for stable prediction, but we only know the qualities and the powers that substances exert, not the essence of the stuff that underlies them. The famous claim associated with him is the rejection of innate ideas and the insistence that knowledge rests on experience. Yet his account does not surrender substance entirely. It simply disguises the substrate behind a mask of qualities. This creates a pragmatic tension. Scientists rely on the language of substances and the causal roles they play. Even though in strict epistemic terms we may only know assembled ideas about the relations of primary qualities, size, shape, motion, rather than any intimate acquaintance with the underlying substrate, David Hume, in a different tone, pushes the problem toward radical skepticism about substantial substances. In Hume's most compact and celebrated formulation, the mind is a bundle of perceptions, a cluster of impressions and ideas that do not themselves require a stable substrate to ground their coherence. The famous phrase, "I am a bundle of perceptions," captures the sense that the self, the subject who experiences, does not reveal a fixed, persistent substance behind the changing stream of sensations. Applied to matter, Hume's skepticism invites a radical relational or qualitative approach. The world consists of a network of perceptions, powers, and relations, and there is no necessary linking substratum that guarantees persistence beyond what the senses deliver. If we extend this to matter, perhaps the rock is not a substance with a fixed ontological status, but a pattern of recurrent associations and regularities among sensible qualities and their relations. The enduring identity of a rock would then rest on the regularity of its experiences and the constancy of its causal relations across time, not on a stubborn substratum that remains identical through all the variations. This is not just an idle hypothetical, it carries practical and philosophical weight. If the bedrock of matter is a field of relations rather than a substance, then questions of persistence, identity, and change take on a new texture. The rock persists because a network of relations endures. The field emerges as the organizing principle that anchors causal regularities, and the mind's ability to predict, measure, and manipulate rests on the stability of those patterns. Hume's critique, read in this light, challenges any naive confidence in a persistent material substrate that seems to do the heavy lifting of reality. On the other hand, many scientists and philosophers push back, arguing that the language of substance remains indispensable for the very practice of science. The language of substances helps us carve nature into intelligible units with predictable behavior, enabling experiment, theory construction, and manipulation in the lab. The field theory that matured through Faraday and Maxwell adds a robust, alternative framework, one that many see as offering a more faithful account of the causal structure of the physical world. Faraday's practice of lines of force and his insistence on the physical reality of the field as the bearer of interactions planted a seed that would grow into a mature ontology in which fields are not mere abstractions but physical entities with energy, momentum, and dynamics. Maxwell's equations codify this view in a way that produces precise predictions about how fields propagate through space and interact with matter. The field, in modern interpretation, becomes the stage on which physical processes unfold. Matter is not so much an inert actor as a pattern of influence within an energetic fabric. The rock becomes a region where the field values arrange themselves into a configuration that produces the observed behavior of the object when placed within the gravitational, electromagnetic, or other relevant fields. We should pause to reflect on several concrete illustrations that bring the field picture to life. The rock, under the field view, is not an isolated, standalone substance with intrinsic masses and charges that simply exist. Instead, the rock's behavior arises out of the interplay of electromagnetic fields and gravitational fields, if we care to include them, that extend through space and interact with the rock's constituents. The magnet's field, the Earth's gravitational field, And quantum fields at the microscale all participate in shaping what we observe. The field around the rock is not merely a background layer, but an active agent that structures how matter behaves, how it vibrates, conducts heat, binds with other materials, or resists deformation. A rock's rigidity, hardness, and spectral features are all partial reflections of the field's influence on the microstructure of matter, yet field theory raises its own questions, especially in relation to the persistence problem that relational theories pose. If the fundamental ground of reality is a network of fields, what guarantees the continued existence of stable objects across time? How do fields account for the individuality of objects, if the rock is just a configuration of fields? What ensures that the rock remains the same rock as time goes by and as its microstructure evolves under stress, heat, or irradiation? The classic field answer is that fields carry dynamical laws, and the objects they organize are stable because the field's configurations tend towards certain patterns that persist under a wide range of conditions. The laws of physics, Maxwell's equations, Einstein's general relativity, the Schrödinger equation in quantum mechanics provide the rules that govern the evolution of field configurations. When you push a rock, you bend the field lines. Those lines respond to the interaction, and the whole system adapts while preserving the overall organizational structure that we continue to identify as rock-like. But then the question arises again, where does the objectness or object identity come from? If the ground is a field rather than a thing, do we owe this object identity to the field's boundary conditions, to the boundary between regions of space where fields differ, or to some deeper substrate that remains stable through field transitions? This is where Kant's reluctance to surrender the noumenon loops back into contemporary debates. Kant would remind us that even as we fuse with the field narrative, our scientific theories are still grounded in the forms of intuition and the categories of understanding that organize experience. The field may be real in the sense that it has measurable effects, can store and transfer energy, and can be described by precise mathematics, but the very idea of a field, the way we conceptualize it, is a product of our cognitive and mathematical framework, and so Kant's caution becomes not a constraint but a guide. We should be mindful of the limits of our ontological commitments and the way our best theories carry us toward, but never quite reach the ultimate ground of reality. In the late 19th and early 20th centuries, the field thesis receives a further radical twist with the advent of relativity. Albert Einstein helps us to see that fields are not mere ambient scaffolding. They are intertwined with space-time geometry itself. The very properties of matter, mass, energy, momentum are intimately related to the geometry of space-time. In Einstein's theory, mass and energy determine the curvature of space-time, and the curvature of space-time in turn guides the motion of matter and energy. The field there is not just something in space, it is part of the fabric of space and time themselves. In this sense, the ontology of fields and the ontology of spacetime become two faces of the same fundamental coin. Mass is not simply an intrinsic property of an object, it is a manifestation of spacetime geometry interacting with energy. The field is thus not a separate substance floating on a stage, but a dynamic pattern woven into the very architecture of the universe. This is perhaps the most sweeping departure from the older substance-centric narrative, the possibility that what counts as matter is not a separate, persisting chunk of something that has intrinsic properties, but a state of the field coupled with the geometry that organizes it. The rock's identity, if nothing else, is a particular pattern within the field given a particular curvature of spacetime. The myriad empirical successes of quantum field theory push the story even further. At the most fundamental levels, we do not have classical particles as independent substances, but excitations of underlying quantum fields. The electron is a quantum excitation of the electron field. Photons are quanta of the electromagnetic field. The ground of reality begins to look less like substance A with properties P, and more like a mosaic of field states whose excitations give rise to what we ordinarily think of as particles. The world, at that scale, looks more like a dynamic web of fields and their excitations than like a shelf full of independent substances. Of course, there are strong counterarguments. The persistent appeal of substance-based language in science should give us pause. Even in quantum field theory, practitioners talk about particles and fields in a pragmatic, almost folk ontology sense. When a physicist speaks of an electron, a positron, a proton, they often think in terms of entities with definite properties like mass and charge, stability, and a track record of reliable interactions. The field story can feel to some like a rebranding of old substance talk under a new mathematical gloss, if a theory still needs stable, localized entities to explain experimental outcomes. Does the field ontology genuinely dissolve the old problem? Or does it only reframe it in more abstract terms? Another counterargument concerns reductionism and the explanatory reach of fields. Fields can elegantly explain forces and interactions. But there are moments when a fieldist must explain what grounds a field's own existence and what constitutes the field's ontological status as independent of the objects to which it is applied. Some philosophers worry that field theories may struggle to explain how fields produce the specific properties of their sources. If a rock is simply a region of a field with a certain energy density, how does one ensure that it is not just a capricious mapping of the field onto matter's microstructure? How does one reconcile field causation with the everyday sense that objects possess causal efficacy without always recourse to a field? Further, there are worries about the explanatory reach of reducing everything to field dynamics. Can a field fully account for the intuitions we have about identity, continuity, and the persistence of objects through time? Or does it just relocate the mystery, now beyond the physical sciences? We can trace the cross-currents that connect to emergentism and to the more unusual forms of grounding. Emergentism offers a synthesis that seeks to handle the best of two worlds. It preserves the reality of higher-level structures and novel properties that appear at larger scales, even while admitting that these structures depend on and are real only within lower-level microstructures. In emerging accounts, mass, charge, and energy remain physical, but the way they cohere and interact at the macro scale can produce qualitatively new phenomena that cannot be completely predicted from the microlevel alone. Consider a crystal lattice above a certain temperature or under particular conditions. The lattice can exhibit emergent properties, frustrated states, symmetry breakings, collective excitations like phonons that are not obvious from the behavior of isolated atoms. The lattice thereby becomes a real, causal actor in its own right, even if its most fundamental microconstituents do not themselves reveal those properties in isolation. Spinoza's monism offers a contrasting form of emergence in its own way. If there is one substance, the emergent properties of mind and body are not independent novelties that arise in a world of separate substances. Rather, they are forms of the same underlying reality manifested through different attributes. Emergence, for Spinoza, might be reinterpreted as the natural differentiation of modes within the selfsame substance, a unity reaching out to form a coherent manifold of appearances. In contemporary terms, one could see Spinoza's project as anticipating a form of ontological holism, in which the many things we observe are grounded in a single ground that cannot be simply reduced to discrete atoms or to independent fields, but rather is the dynamic fabric in which all modes unfold. We should also consider the mind-matter relation as a thread running through the entire discussion. The problem of how matter is related to mind, how consciousness interacts with the physical world, or whether mind is an emergent feature of matter, has haunted philosophy since Descartes. The field and dynamical views, with their insistence on energy, causation, and pattern, offer new resources for approaching this ancient issue. Some theorists propose a form of neutral monism or epiphenomenalism, in which both mind and matter emerge from a deeper, more fundamental field-like substrate that is not purely physical in the everyday sense. Others propose non-reductive physicalism, where mental properties supervene on physical states but cannot be fully reduced to them. The field perspective might enrich those discussions by suggesting how mental states could be realized as particular field configurations or as aspects of space-time geometry that correspond to information processing in complex systems. As we move toward modern interpretations, we encounter the work of Einstein, who in his general theory of relativity reframes mass, energy, and space-time in a unity that dissolves rigid distinctions between field and substance. Mass is a property related to energy. Energy is something that curves space-time, and space-time geometry itself dictates the motion of matter and radiation. This picture intensifies the sense that reality is not bounded by a single category of ground. Instead, the ontology of the 20th century moves toward a more integrated, relational, and dynamic cosmos in which the fabric of space and time is as much an actor as the objects that populate it. The mass-energy content of a region of space-time becomes a determinant of curvature, a property that in turn modifies how fields propagate and how objects move. The rock is not merely a passive chunk of stuff, but a region in a field of curvature. This reorientation invites us to revise not only what we mean by matter, but what counts as agency, causation, and persistence across time. The field-centered turn, while deeply explanatory and mathematically powerful, invites further critical scrutiny. It is not enough to show that fields can carry energy and mediate forces. We must also account for how field ontologies relate to the everyday language of objects and substances. The explanatory role of such hierarchies matters for how we interpret scientific theories and how we teach them. There is a practical sense in which field language is more accurate at the micro scale and at the cosmological scale, while the language of substances remains vitally useful for engineering, laboratory work, and everyday experience. If we talk about rocks or crystals in a field framework, we still need to identify the specific field configurations that correspond to these macroscopic entities. In other words, fields can explain a subset of phenomena, but the whole of what is a rock requires a story about microstructure, boundary conditions, and emergent properties that are robust enough to appear as stable. Macroscopic objects in the world. The modern survey that we have undertaken in this segment would be incomplete without listening to the counterarguments that persist in the broader philosophy of physics. One such objection is the persistence problem for relations or fields. How do we account for an object's continued existence as the state of the field changes, or as measurements reveal different patterns of energy distribution? The field must offer a robust account of identity and persistence that is not simply dependent on a fixed substrate. A second key objection concerns explanatory reach. Can field theories truly explain the behavior of matter in all contexts, including those where classical intuitions about objects and substances have proven particularly tractable? Yet a third challenge concerns the idea of reduction. If quantum field theory reveals that particles are excitations of fields, and if then a purely field-based ontology seems to be all-encompassing, what becomes of the intuitive sense of thinghood that accompanies everyday experience? And if the noumenal ground remains as Kant suggested, even a field theory may still not reach the ultimate ground of reality. In response, many defenders of the field approach argue that the best explanation is often the most parsimonious and powerful in predictive accuracy. If a single mathematical framework, Maxwell's equations, or the Einstein field equations, or the quantum field theoretical formalism, permits us to predict phenomena across scales with stunning precision, then that framework counts as a robust physical ontology. The field is not simply a metaphor, it is alive. Dynamic structure that can be experimentally probed, manipulated, and integrated with observation. The reason we care about fields and not just about substances is that fields make sense of causation across distances, of energy transfer and momentum flow, and of how geometry and dynamics co-create what we experience as the physical world. The explanations offered by field theory have real intellectual power. They connect deeply with experimental data, unify disparate phenomena, and offer a coherent language for discussing the most advanced theories in physics. Having arrived at this juncture, we can now look at a few cross-references to connect this exploration to broader conversations in philosophy and science. First, the philosophy of physics is the natural home for debates about substance, field, and reality. Philosophers like Mario Bunge, Bas van Fraassen, Tim Maudlin, and others have argued for field-oriented or relational frameworks or have defended robust forms of scientific realism about the entities our theories posit. They point to the interplay between mathematics and ontology, how equations take on a life of their own, guiding our understanding of the world. While our ontological commitments must not outpace the empirical content of those equations, the field viewpoint aligns naturally with a scientific realism that emphasizes structures and relations as real, while still acknowledging that our language of things is a useful and sometimes necessary simplification for human cognitive processing. Second, the ontology of fields invites a careful engagement with the mind-matter problem. If the world is ultimately field-structured, does that leave us with a new form of interaction between mind and matter that is more tractable or more problematic? Some philosophers have turned toward informational or causal novel approaches to mind, suggesting that consciousness might correspond to particular field states or patterns in a broader information processing field. Others insist that mind remains a special kind of cause, non-physical in virtue of our own categories of understanding, or that it emerges from the complex patterns of matter and energy in ways that cannot be fully reduced to field dynamics. Third, there is a robust historical thread connecting this discussion to ethical, aesthetic, and political thought. How we conceive matter affects how we conceive of technology, environmental stewardship, and our own sense of place within the cosmos. If matter is a field-laden fabric that binds the universe, then ecological interdependence takes on a new vindication. Not only are organisms connected through food chains and ecosystems, but the very fields that shape them, electromagnetic, gravitational, and quantum fields bind the world in a larger, more intricate choreography. The recognition that mass energy curves spacetime or that fields mediate forces across space invites a humility about the scale and power of human agency. And it elevates the responsibility we bear when we intervene with technologies that manipulate the physical substrate of reality. To illustrate the themes we've traced in a few concrete vignettes, let us consider two additional examples that illuminate the theory and application relationship in memorable ways. First, imagine a rock as a conventional material substance in the everyday sense. We can physically pick up the rock, weigh it, and observe its reaction to a hammer blow. Within a substance-based explanatory frame, we would describe the rock as a durable chunk of matter with a definite mass, a density that emerges from the arrangement of molecules, crystalline structure, and bonding energies. The rock's stability rests on the enduring substrate of matter, even as microlevel rearrangements occur under the influence of stress and temperature. Yet even within this familiar frame, we glimpse the field's influence. The rock sits in a gravitational field. A magnetic field does not necessarily anchor the rock, but can influence its magnetization in certain minerals. And the surrounding environment imposes boundary conditions that shape how the rock interacts with energy it absorbs or emits. The field is there, but often it operates behind the scenes. And substance-based language remains a practical tool for engineering and everyday talk. Second, consider a crystal lattice, say, a diamond or a quartz crystal. A lattice is an emergent order arising from microstructure, arranged into a regular, repeating pattern. The lattice's properties, its optical characteristics, its phonon modes, its thermal conductivity, emerge from the microlevel arrangement. Yet they cannot be wholly reduced to the behavior of individual atoms. Emergentism has us attend to this phenomenon. Why do crystals exhibit properties that are qualitatively new compared to random arrangements of atoms? The ordered lattice is a robust example of how macroscale properties arise from microscale interactions. Here, the philosophical question is not simply about whether the lattice is a substance or a field. It is about how to categorize the lattice's robust, novel properties and whether their existence demands a new kind of ontological category that sits atop the microlevel description. Emergentism argues that it does. The crystal lattice is both physically real and epistemically novel. Its descriptive vocabulary, phonons, Bragg diffraction, and crystal symmetry captures genuine features of the world that are not reducible to a simple catalog of microstates. A separate but closely related example comes from magnetism. A magnetic field is something that structures matter rather than something contained inside it. When we say the field exists, we are making a direct claim about a causal structure that can influence material behavior. The rock's electrons may align under certain conditions, giving rise to magnetization. The question, then, is whether the magnetic field is an ambient force or an intrinsic part of the rock's reality. The field view says that the field is a real, dynamical entity that exists in space and time and interacts with matter to produce measurable effects. In this sense, the magnetic field is not simply a property of the rock but a relational structure in which both the rock and the field participate. An additional modern touchpoint is the quantum field theory that underpins our understanding of subatomic particles. In quantum field theory, particles arise as excitations of underlying fields, and the fields themselves are the carriers of energy, momentum, and information. The electron is not a little ball with an intrinsic charge. It is a quantum excitation of the electron field with properties that emerge when the field is in particular states. The distinction between substance and field is refracted through the mathematics of quantum fields. We talk about particles, but those particles are not tiny billiard balls, they are quantum states of fields. This realization reframes our metaphysical question. If the world's fundamental constituents are fields, does it make sense to call them substances at all? The philosophical implications are still contested, but the field-centric view remains one of the most robust anchors for contemporary physics, providing a coherent way to model forces, interactions, and the creation of new properties as patterns emerge from field configurations and their dynamics. If we extend our gaze to the broader implications, there is a continuing conversation about whether the matter problem ultimately defers to a more fundamental ontology, or whether there is a sense in which each framework contains a grain of truth. The field approach plausibly captures a central dimension of physical reality, the relational, gestural, and dynamic side of matter's behavior. The substance-based approach preserves a sense of enduring entities that are useful for describing, predicting, and manipulating the material world, and it helps preserve the everyday vocabulary through which science communicates with laypeople, technicians, and students. Emergentism, meanwhile, preserves the importance of higher-level organization and recognizes that the world exhibits qualitatively new features at larger scales that are not obviously reducible to micro-level laws. In closing this portion of our exploration, we must acknowledge that the matter problem is as much a story about language and interpretation as it is about physics and metaphysics. The way we name things, the rock, the field, the lattice, the spacetime, affects how we think about their nature and their role in the cosmos. The same object can be described in a way that highlights its substance, or in a way that highlights its fields, or in a way that emphasizes emergent properties and patterns. Each description offers a legitimate vantage point, and each has its own explanatory fruit. The challenge for a mature philosophy of matter is not to pick one of these pictures as the ultimate true ontology and then defend it to the death. The challenge is to illuminate the strengths and limitations of each approach, to illuminate where they converge, and to clarify where they diverge in ways that bear on our understanding of the nature of reality, the status of objects, and the ultimate ground of what exists. We should also emphasize the broader cross-references that enrich this discussion. In the philosophy of physics, the debate about substance versus field connects to questions about the interpretation of quantum mechanics, the ontology of spacetime, and the status of causality in a relativistic and quantum universe. The ontology of fields ties into debates about the nature of causal influence in a world where space and time themselves are dynamic and where forces are mediated by fields rather than instantaneous action at a distance. The mind-matter relation features not only in classic dualisms, but in the modern critique of functionalism and property dualism. As scientists and philosophers attempt to connect conscious experience with the dynamical states of physical systems, possibly realized as complex field configurations or emergent properties at higher levels of organization. Finally, historical anecdotes, the field's visualization in Faraday's experiments, Maxwell's mathematical synthesis, Spinoza's monistic grandeur, Kant's noumenal caution, and Einstein's spacetime revolution provide not only riveting stories, but a map of how our conceptual apparatus has evolved in response to deep empirical discoveries. To bring together these threads with a concluding flourish, let us return to the core questions we set out to explore. Must matter be grounded in a persistent substance, an enduring substratum that bears the weight of all its properties? Or can it be grounded more fundamentally in relations, in fields in the web of interactions that define the structure of reality? The answers are not simple or singular. There are compelling reasons to preserve a robust substance ontology, for it gives us a reliable scaffold for describing the stable, manipulable world we encounter daily. There are equally compelling reasons to embrace a field-centric ontology, for the field explains the causal structure of the universe, the way forces travel, how energy moves, and how the geometry of spacetime conditions all physical processes. Emergentist accounts offer a middle course, acknowledging that the world contains levels of organization in which novel features arise that cannot be reduced to micro-level laws alone, while still insisting that those levels are grounded in the microstructure that underlies them. And yet, in the end, perhaps the deeper moral lies not in choosing between these positions, but in recognizing how they illuminate one another. The field view pushes us to recognize how the fabric of reality is woven with relational structure. The substance view reminds us of the importance of persistence, stability, and the everyday language in which scientists and laypeople alike think about the world. The emergent view invites humility before the wealth of patterns that appear when many pieces come together under the right conditions. The great thinkers we have encountered, Descartes with his extended substance, Aristotle with his form and matter, Spinoza with his one substance, Kant with his noumenal horizon, the empiricists with their skepticism, Faraday and Maxwell with their field-born insights, Einstein with his space-time-coupled masses, each offers a different lens through which to view the same landscape. The question of matter is not settled once and for all. It is a living dialogue about what grounds reality, what counts as persistence, how fields and forces shape what we can know, and how we must live with the consequences of these theories in science, technology, and everyday life. As this section closes, I want you to carry forward a few markers. First, keep in view the distinction between what grounds persistence, the substrate, and what organizes phenomena, the form, the field, or the pattern. Second, notice how the language we use, substance, field, relation, emergent property, often reveals not only our metaphysical commitments but also the practical pressures of scientific practice. Third, allow room for a pluralist sensibility. There is wisdom in admitting that the best account for a particular problem may shift with scale and context. A rock at the human scale might be best described through a substance-based lens with emergent properties, While at the micro scale, the field description may be more fitting, and at the cosmological scale, gravitation and spacetime dynamics demand a field-like or geometric thinking. Finally, I want to leave you with a set of reflective prompts that you can carry into your own exploration of the philosophy of matter. Prompts that connect the historical arc to the concerns of contemporary science and to the broader philosophical questions about knowledge, reality, and value. If matter is best described as a field, what becomes of our ordinary sense of discrete objects having an intrinsic identity independent of their relations? Can we maintain objecthood and relational ground without sacrificing coherence? If Spinoza's monism is true in a deep sense, what becomes of the long-standing intuition that mind and body are separate kinds of things? Does monism illuminate the mind-body problem, or does it dissolve it into a broader unity that cannot be easily felt or experienced in ordinary life? How do mass, energy, and charge function differently depending on whether they are interpreted within a substance ontology or within a field ontology? How does this affect how we model the interactions of matter at different scales? What conceptual tools does emergentism offer for reconciling the reliability of higher-level theories, like solid-state physics, crystallography, and chemistry with a physically grounded microtheory? To what extent does Kant's insistence on noumena and appearances limit or enable our scientific ambitions? Does it prevent us from reaching reality as it really is? Or does it safeguard us from overreaching claims and misapprehensions? How do Faraday's lines of force, Maxwell's equations, and Einstein's spacetime frame our modern sense of causation, space, and time? In what ways do these historical shifts illuminate or complicate our current understanding of the nature of matter? When we adopt a field ontology, how should we interpret everyday scientific language? Do we still have a legitimate place for talk of substances, interfaces, and boundaries, or should we replace those with a vocabulary of fields, modes, and excitations? How do quantum fields transform the metaphysical landscape of matter? If particles are excitations of fields, what becomes the status of the classic substance at the heart of our most intuitive theories? And finally, what responsibilities arise from our expanding ontological commitments? If reality is a web of fields, interactions, and spacetime geometry, how should we cultivate humility, prudence, and care in our technological practices and in our social institutions? This is not merely a gleaming panorama of ideas. It is a call to contemplation about how we live with the world. The matter question is not a sterile academic dispute confined to the pages of a philosopher's notebook. It is an invitation to see the very fabric of the world we inhabit in a new light. The rock in the stream and the crystal lattice are not just objects. They are manifestations of a deeper pattern of reality. A pattern whose precise shape depends on the scale of inquiry and the theoretical lens we apply. Geography, physics, metaphysics, and the human longing to know are braided together in this question: how does matter exist? And what does that existence require of us as knowers and as agents? The travel from Aristotle's form and matter to Kant's noumena, from Descartes' extended substance to Faraday's lines of force, from Maxwell's field equations to Einstein's spacetime geometry, is not simply a story of increasing sophistication. It is a narrative of how our most basic intuitions about what exists, what can be weighed, measured, touched, or imagined are continually revised, refined, and sometimes radically transformed by the demands of science and the questions of philosophy. In the next part of our journey, we will turn toward concrete applications and modern debates, including a deeper engagement with contemporary positions such as Spinoza's monism, reframed for contemporary metaphysics, and emergentism's nuanced take on how novel properties arise from complex systems. We will examine how these theories fare when confronted with cutting-edge physics, such as quantum field theory and the spacetime-based description of gravitation, and we will look at how different ontologies influence the way we model problems, design experiments, and interpret results. We will also revisit the two or more counterarguments we touched on here with fresh case studies and thought experiments that illuminate the strengths and limitations of each framework. For now, I invite you to reflect on the enduring question: what is the ultimate ground of reality when we talk about matter? Is it a substance that persists through time? Is it a field that structures the world and carries forces across space? Or is it something else? A ground that emerges only when we bring together a constellation of ideas from science, philosophy, and everyday life. Each tradition offers a coherent account with persuasive insights, and each also leaves open critical questions that invite ongoing inquiry. The history of the metaphysics of matter is, in this sense, the history of how human beings have learned to see the cosmos. It is a story about how we move from the old to the new, how we test our deepest assumptions against the stubborn facts of nature, and how we attempt to reconcile the mind's hunger for unity with the world's stubborn multiplicity. And as we keep asking, keep listening, and keep testing, the matter of matter will continue to reveal itself in new and surprising ways, inviting us to think with greater clarity about what there is, what it means for something to be, and what sort of ground underwrites the entire enterprise of science, philosophy, and life itself. We end this segment with a reminder of the cross-references that will deepen your understanding as you move forward. The philosophy of physics will reappear in our discussions of ontology and causation. The ontology of fields will connect with debates in the mind-matter relation that we will unfold in later sections, and the historical anecdotes, Faraday's lines of force, Maxwell's synthesis, Spinoza's single substance, Kant's noumenal horizon, and Einstein's spacetime will serve as beacons guiding your own explorations and helping you see how a branch of thought grows through dialogue with both experiment and argument. The section you have just read is designed to be a thorough, reflective walk through the main trajectories of metaphysical theories of matter, and it should equip you to recognize the landscape, to identify where you yourself stand, and to understand what remains to be argued about when we speak about the real stuff of the world. If you wish, we can now move into a practical exploration of how these ideas influence specific domains, philosophy of science, metaphysical realism, and contemporary debates about the nature of fields and emergent phenomena, or proceed to a closer reading of primary sources and their interpretive histories to ground your understanding even more firmly in the voices of the past. The choice is yours. And the journey continues. Matter in physics does not simply exist as a static, stubborn stuff that resists change. It moves, it resonates, it fails to fit into our earliest categories, and then it reshapes those categories so thoroughly that our language, our metaphors, and even our most cherished intuitions must bend. In this segment, we travel from the old grain pictures of ordinary matter, the little billiard ball atoms that Dalton imagined, to the modern, vibrant picture of a universe woven from fields, where mass, energy, and information mingle in ways that would have sounded like science fiction to a Victorian natural philosopher. We will follow the through lines of theory and experiment, the way a single insight after another interrupts our common sense, and the way philosophy, in dialogue with physics, tries to decide what to count as the nature of matter. And we will do more than recount milestones. We will explore what these milestones do to our deepest questions. What is matter? And what is its ground? Is matter a substance, a process, a pattern of relations, or something else entirely? How do theories claim to describe reality? And in what sense do they reveal or merely model that reality? What does it mean to say that mass and energy are interchangeable, or that a field is the true substrate of the physical world? To begin, let us step back to the era when matter still wore the simple mask of solidity, color, and weight, and philosophers could reasonably imagine that the essence of matter lay in tiny, indivisible particles. The story begins with John Dalton, who in the early 19th century proposed a bold, systematic picture. Matter is composed of atoms, indivisible in principle, arranged in chemical compounds in fixed ratios. Atomic theory was not just a vindication of chemistry's empirical rules, it was a metaphysical move. Dalton's atoms were the ultimate bearers of identity for substances. Each kind of matter carried its own distinct kind of atom, a basic unit that could not be further reduced within the chemical realm. This was a triumph of a certain kind of realism. Matter is something that endures, that has a discrete, countable substratum that could be named and tracked across experiments. When we see relationships among elements, we are seeing how those atoms combine, rearrange, and sometimes transmute in spectacular, telltale ways, in Dalton's mind and in the minds of many of his contemporaries. To know the matter of something was to know its smallest constituent and the laws by which those constituents interacted. But we do not linger long in the parlor of Dalton's model, the laboratory. The crucible of early 20th century science began to reveal a different picture, one in which the atoms were not the final word, and the matter they were built from revealed deeper layers of structure. The first shock came with the discovery of the electron by J. Thomson in 1897. The image of matter as a mere cluster of billiard ball atoms began to fracture. If there are charged particles that can be deflected, if electrical currents can bend in magnetic fields, perhaps the material substrate is more a sea of activity than a rigid grainy substance. An electron is not a little ball with a fixed trajectory so much as a dynamical rip in the field of electromagnetic interactions. Yet the revolutionary move still preserved a sense of substance in place. There were discrete particles, albeit non-classical, that carried charge and mass and obeyed quantum and relativistic rules. Shortly after, the Rutherford scattering experiments, culminating in the famous gold foil experiment, Press the next wave of upheaval. The alpha particles shot at a thin gold foil sometimes passed through, sometimes glided by with little deflection, and occasionally scattered at large angles. The conclusion was stark. Most of the mass and the positive charge of the atom is concentrated in a tiny nucleus, surrounded by electrons in space. This picture, nucleus, electrons, a planetary-like arrangement, carried the grandeur of a mechanical analogy. Matter had structure at the smallest scales. There were regions of dense, positive charge, then the electrons with their enigmatic behavior. Yet even here, the philosophical impulse to carve out substance persisted. The atom, a collection of constituents with properties that could be measured and predicted, seemed to confirm a certain realist insistence. There is an underlying material core that persists through changes in state, that can be isolated experientially by chemical and spectroscopic methods. And then came the quantum revolution, which did not merely add a few corrections to Dalton's atom, but ripped up the stage directions of how we understand matter altogether. The first great pivot was Planck's quantization, a heuristic device that turned the continuous spectrum of radiation into something that came in discrete units, the quanta of action. E equals h times frequency. Planck's gesture did not at first claim to describe matter itself. It described the interaction between matter and radiation. But the philosophical ripples were immediate. If energy exchange is quantized, if light behaves as if made of particles as well as waves, if the same system can exhibit wave-like interference and particle-like localization, then our most basic taxonomy, matter is something that has an inherent, continuous wetness of energy, began to crack. The old intuition that matter is a simple, continuous substance could no longer be assumed. The ground shifts from a ground of sameness to a ground of discrete, probabilistic events that manifest in experiments. Einstein's 1905 explanation of the photoelectric effect, light quanta interacting with electrons to eject them from a material surface, took a similar leap. He treated light as if it consisted of discrete quanta of energy, each carrying an amount h nu. The result was not just a formula about electrons, it was a turning point in how we imagine light and matter interacting. If light has particle-like properties under certain circumstances, if energy exchange occurs in indivisible quanta, then the boundary between what counts as matter and what counts as radiation loosens. The world again refuses to be a simple set of mutually exclusive categories. The same fundamental interactions appear to inhabit multiple descriptive styles, sometimes waves, sometimes particles, sometimes something in between in the phenomenon of interference and diffraction. Bohr's model of the atom, with quantized orbits and spectral lines, offered a concrete, testable account of atomic stability and emission. Yet Bohr's achievement was not merely a numerical trick. It embedded a deeper philosophical claim. The behavior of the microscopic constituents of matter is not fully captured by classical trajectories and intuitive pictures. The atom could be described through discrete energy levels, through the probability of finding an electron in a particular region of space, through transitions that emit or absorb photons of specific energies. The method of description, what counts as an explanatory mechanism, is shifting from a purely causal, clockwork story to one that requires new metaphysical commitments about states, possibilities, and the role of observation. This is a crucial pivot for philosophy. Explanations in physics move from statements about how things push and pull to statements about the structure of the theories we use to organize and predict measurements. Schrödinger's wave mechanics, introduced in 1926, anchored a further transformation. The mathematical state of a system is described by a wave function, a probability amplitude that encodes what we can know about the system. The wave function is not a classical field, it is a different kind of entity, an information-laden tool that yields probabilities for the outcomes of measurements. The wave function's status, however, quickly became a central philosophical question. Is it ontic, something real out there in the world, or is it epistemic, a statement about our knowledge, our information, or our beliefs about the system? The Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg, tended toward an epistemic reading, or at least a pragmatic one. The formalism yields predictions for experiments, and questions about an underlying reality beyond the measurement apparatus may be beyond science or not meaningful in the same sense. The many worlds interpretation, championed by Hugh Everett later in the century, offered an ontic reading of the wave function. The universal wave function is real, and all branches of the wave function correspond to actual decohered worlds. Bohmian mechanics, another contender, kept a robust realism by positing a real guiding wave and actual particle trajectories, thus preserving a kind of subclassical determinism. The philosophical drama here is not a mere footnote. It is a confrontation about what it means to say a theory describes matter itself or merely describes the behavior of matter under observation. And across these shifts, the relativistic lens of Einstein reframed mass and spacetime in a way that compelled philosophers to rethink the very substrate of matter. Mass ceased to be a simple additive property carried by a little resistant body. It became a form of energy content, a curvature of spacetime that interacts with gravity, and a part of a four-dimensional fabric in which energy and momentum are inextricably bound to the geometry of the universe. E equals mc2 is not simply a formula linking mass and energy. It is a window into a metaphysical shift. The same substance is not fixed in a way that makes it obviously material. Instead, the same physical entity can be understood in multiple, highly constrained, context-sensitive ways, often revealing that mass is not a primitive quality, but a feature emergent from deeper symmetries and interactions. And spacetime, far from being a passive stage, becomes an arena in which matter and energy tell stories about their relations and their histories. From there arises the quantum field theory that would eventually form the backbone of the Standard Model. The counterintuitive move here is not merely technical but ontological. What we call matter, what we call particles, and what we call forces are all emergent from and intimately described by fields that extend through space and time. The electromagnetic field, the electron field, and the quark fields are not just convenient languages for describing a world of little objects. They are the real scaffolding of physical reality in this view. Particles are excitations of underlying fields, resonances that appear when fields are excited in particular patterns, and the interactions among fields, gauge interactions, become the laws by which the universe organizes itself. In this framework, the Higgs field is a particularly dramatic actor, a field permeating all space, whose interactions with certain particles give them mass via the Higgs mechanism. The discovery of the Higgs boson in 2012 at the Large Hadron Collider did not merely add a new particle to the pantheon. It confirmed a mechanism by which mass arises from symmetry breaking in a field that pervades the cosmos. If the Higgs is the key to why some particles have mass, the vacuum energy and the structure of the vacuum become themselves worthy of ontological attention. What is the vacuum? Is it nothing at all, or is it a rich, fluctuating medium with energy that contributes to gravitational dynamics at cosmological scales? It is essential to bear in mind that this shift toward fields does not erase the old intuition about matter, it reframes it. The field-theoretic view insists that what we once counted as matter, substantial, localized chunks are now understood as patterns of field excitations and their interactions. The material world is felt most tangibly in the solidity of a rock, the texture of a metal, the warmth of a hand, but on the theoretical plane, the rock's stubborn properties emerge from the interactions of countless field configurations, the superposition of possibilities, the symmetry structures that permit or forbid certain interactions, and the dynamics of vacuum fluctuations. The ground has become more elaborate, more relational, and perhaps more mysterious than the classical picture allowed, and yet, paradoxically, the predictive power of this field-centered ontology is remarkably robust. The Standard Model, for all its acknowledged incompleteness, dark matter, dark energy, gravity not yet fully integrated with quantum field theory, accounts for a stunning array of experimental results with a single coherent mathematical architecture. It is a triumph of human intellect that has to be stated with humility. We can describe, with extraordinary precision, a great range of phenomena by positing that matter is not simply little billiard balls, nor a single kind of substance, but a spectrum of fields whose excitations behave in ways that sometimes resemble particles and sometimes resemble waves. We must also reflect on the role of relativity. Einstein's theory of special relativity reframed mass, energy, and motion in terms of spacetime structure. Nothing can travel faster than light, simultaneity is relative, and energy and momentum transform in ways that fuse into a four-vector. General relativity extends this to gravitation, describing spacetime as curved by energy and matter. In this light, matter is not merely a thing in space, it is a pattern of energy distribution that informs the geometry around it. The concept of mass becomes a kind of shorthand for a particular signature on the geometry, the inertia to acceleration, the gravitational influence it exercises. The ontological status of mass becomes entangled with spacetime geometry itself. This is a striking shift. Matter is not a thing that sits inside space. Matter participates in the construction of space, and the geometry of space tells matter how to move. The philosophical stakes are high. If space and time are not the fixed backdrop but the stage and stagehand intertwined with matter, Then our old metaphysical pictures, substance as a stubborn, intrinsic core, must be reconsidered, perhaps replaced by a relational, transactional, or structural reading of what it means for something to be in the world. And yet, throughout this century-long evolution, a stubborn puzzle has persisted: the measurement problem. In a world where the wave function provides a way to calculate probabilities, where a field can be an underlying substrate, how does the act of measurement produce the definite outcomes we experience? The Copenhagen interpretation invites us to accept that quantum probabilities become real only through observation, and many physicists have pushed back against this feeling that observation wields a special ontological status. The many worlds interpretation, by insisting that the universal wave function never collapses, forces us to accept an immense, perhaps infinite, proliferation of parallel branches in which all possible outcomes actually occur. Bohmian mechanics preserves determinism through a deterministic pilot wave guiding particle trajectories. Yet it does so with a radical redrawing of how to think about particles and their histories. The upshot is stark. Different philosophical commitments pull the physics in different directions about what the equations are saying about the nature of matter and reality itself. A particularly important modern development within this debate is decoherence. Decoherence explains, in a precise physical mechanism, how quantum systems interacting with their environments lose their ability to maintain coherent superpositions in macroscopic contexts. It provides a bridge between the quantum world and the classical world we experience, showing that the classical realm emerges not by the collapse of the wave function, but by the rapid spreading of quantum information into environmental degrees of freedom. Decoherence does not by itself solve the measurement problem or decide which interpretation is correct. Rather, it clarifies how the appearance of definite outcomes arises from the complex interactions of many degrees of freedom. It supplies a naturalized explanation for why classical objects appear to behave according to Newtonian laws, even though their microscale underpinnings are inherently quantum. The philosophical implication is that the boundary between matter as a substance and matter as a behavior is not straightforward. Rather, matter can be seen as a pattern of persistent regularities that survive drastic changes in scale and description, maintained by the structure of information and the environment that sustains those patterns. If we push outward to the real-world applications, the theory begins to feel less abstract and more tangible. The double-slit experiment, perhaps the most famous demonstration of wave-particle duality, shows that electrons or photons can produce interference patterns when not measured for path, as if they were waves, yet when we attempt to ascertain which path they took, the interference dissolves and the particle-like distribution re-emerges. The lesson for ontology is not simply that particles can act like waves, rather, it is that what counts as an object with definite properties depends on the experimental context, and this in turn reveals a deep coupling between the measurement process, the theory, and the world we are trying to describe. This challenges the classical insistence that objects possess intrinsic properties independent of observation. It nudges us toward a more relational or context-dependent ontology of matter. Quantum tunneling provides another striking demonstration of the non-classical nature of matter. A particle encounters a barrier that classically would be impenetrable. Yet quantum mechanics offers a non-zero probability of appearing on the other side. Tunneling undergirds many technological advances, from electronic components to the nuclear fusion in stars. The world is not limited by classical energy barriers in the way our everyday experiences would suggest. Then there are macroscopic quantum states, superconductivity and Bose-Einstein condensates, where large collections of particles occupy a single quantum state, moving with coherence across macroscopic distances. The idea that a group of trillions of electrons can behave in unison as if they were a single entity is a striking demonstration that matter, at its most fundamental, does not require us to cling to the old idea of a multitude of discrete, isolated particles. Rather, there is a coherent, collective behavior that transcends mere aggregation. In this sense, matter can be thought of as a field-driven phenomenon whose most dramatic properties appear when many degrees of freedom become highly correlated. The Higgs mechanism, more than a mere theoretical trick, offers a concrete explanation for how certain particles acquire mass, endowing the standard model with predictive power that has withstood decades of experimental scrutiny. The Higgs field pervades all of space, and the interaction with it is what yields mass for W and Z bosons and for fermions through Yukawa couplings. The experimental discovery of the Higgs boson, itself a triumph of massive experimental effort and theoretical clarity, is more than a checkbox in a theory. It is a moment of philosophical insight. Even the property of having mass is not an intrinsic attribute of a particle in isolation, but a relational feature arising out of a particle's interaction with a pervasive field, the vacuum. 2 has a rich character in quantum field theory. It is not merely the absence of matter. It is a state with fluctuations, a sea of energy, a complicated structure that can influence particle masses, cosmology, and the very fabric of spacetime via effects such as vacuum energy and the cosmological constant. The vacuum energy problem. The dramatic discrepancy between naive quantum estimates and observed cosmological acceleration invites a deep philosophical reflection on what nothingness means in a theory that is, at its core, about fields and interactions rather than discrete, inherent substances. In light of this historical arc, we can articulate several central arguments about the ontology of matter that physics has pressed into philosophical attention. The wave-particle duality demands a rethinking of whether matter must be strictly one thing in one sense. It suggests that the same entity can display wave-like and particle-like features depending on the experimental arrangement, and that the ontological category of matter may be properly understood as a tapestry of potentialities that are actualized in contexts of measurement. The status of the wave function itself invites debate. Is it a real physical evolution of a system, or a representation of our knowledge, or something even more fundamental, an abstract encoding of information about correlations? The field-centric view reframes the problem. If all matter and forces are manifestations of fields, then what we call substance may be less fundamental than the network of relations and the dynamical laws governing those relations. The mass-energy equivalence is a powerful reminder that rigid categories like substance and energy are not impermeable. Mass and energy are two sides of the same coin, convertible under the right transformations and contexts, and their equivalence reveals the deep unity of what we call physical reality. The concept of the vacuum as a real physical substrate shifts our metaphysical expectations. Nothingness is not the opposite of reality, rather. A positive structure can exist in what classical thought would call absence. The Higgs field embodies this shift by providing a mechanism through which otherwise massless particles become endowed with mass through interaction. A reminder that something as seemingly concrete as mass can be relational and emergent. Of course, this is not a triumph without appreciable counterarguments. There remain strong tensions between classical intuition and quantum reality. The mathematicians dream of a single, all-encompassing final theory must still contend with the apparently probabilistic character of quantum outcomes, and with interpretive options that range from anti-realist practicalities, where theories merely organize observations, to realist, ontologically heavy proposals which treat quantum states as real physical entities. The status of the wave function continues to be hotly debated. Is it a description of reality itself, or a reflection of our information about reality, or something even more elusive like a structure in a higher-order theory? The many worlds view is spectacular in its ambition. No wave function collapse. All outcomes realized, but it challenges our understanding of probability, identity, and personal continuity across branching worlds in ways that many find uncomfortable or implausible. The Bohmian program preserves a robust notion of underlying realism and determinism, yet it introduces a non-local guiding equation that strains our sense of locality and intuitive causality. The Copenhagen pragmatists argue that physics proceeds by giving us predictions that work, and that questions about modality beyond what experiments show may be either meaningless or dangerous philosophical overreach. This plurality of interpretations is not a failure of science. It is a sign that the deepest questions about what matter is, what it is to be a thing, what it means for something to have a property, how to relate a model to reality, are still live issues at the heart of the enterprise. From the historical vantage, a handful of episodes anchor these debates in human storytelling. Planck's response to the ultraviolet catastrophe, an insoluble problem for classical physics that appeared as a spectrum, unjustifiably predicting infinite energy at short wavelengths, was not just a technical fix. It was a radical rethinking of the assumption that energy exchange is continuous. The idea that energy is quantized in units of h-nu offered a new grammar for describing the physical world and opened the door to subsequent quantum mechanics. In the same spirit, Rutherford's discovery that most of the atom is empty space but with a tiny, dense nucleus reframed the core of matter. The world becomes a space of potentialities, fields, and interactions rather than an assembly of pigeons in a tiny marble bag. Einstein's photoelectric effect, where light interacts with matter in a quantized way, provided a crucial bridge between light and matter, enlightening the shared features of the micro-world. And the Dirac equation, uniting quantum mechanics with special relativity, gave us the first coherent account of relativistic quantum fields, predicting antimatter and weaving together two of the great revolutions into a single mathematical fabric. The historical anecdotes are not just stories of experiments and equations. They are stories about how people came to understand that what we call matter is a boundary-laden, context-dependent, richly structured phenomenon. To ground these reflections more concretely in primary voices, consider a few historically charged lines that echo the philosophical mood. Albert Einstein, well known for his provocative insistence on the independence of experimental reality from our prejudices, once observed a sentiment that still resonates in today's debates: God does not play dice with the universe. This famous assertion signals a moment when a scientist articulates a preference for a world that can be described with objective clarity, a world not left to the fickleness of chance. Yet the quantum experiments of Planck, Bohr, and Schrödinger, and even the later insistence of quantum information theorists, challenge us to ask whether the demand for determinism is a necessary condition of truth rather than a historical hangover of classical thinking. A more reflective, perhaps less dramatic, but equally robust set of reflections comes from the physicist's own confession that we do not understand quantum mechanics fully, even after decades of work. Richard Feynman is famous for saying, "I think I can safely say that no one understands quantum mechanics." This is not a cynical confession of ignorance. It is a candid acknowledgement of the depth and subtlety of the theory. The point is not to undermine the legitimacy of quantum theory, but to underline the epistemic humility appropriate to a theory whose predictions are stunningly precise, yet whose interpretation remains contestable. The sentiment resonates with a broader philosophical mood. Science progresses by crafting models that reliably anticipate experiments. While the ontological status of those models, what they reveal about the true nature of reality, remains a matter of interpretation, debate, and continued inquiry. As we trace these ideas toward modern inquiries, we encounter a constellation of cross-references that enrich our understanding. The metaphysical debates about substance, properties, and causation that have been active in philosophy for centuries do not disappear in the laboratory. They are reframed, they are pushed into new shapes by the demands of quantum field theory and quantum information. The realism or anti-realism debates: do our theories uncover mind-independent truth? Or do they primarily organize our observations? Are not academic luxuries. They bear directly on how we understand the matter that makes up the world. The philosophy of science debates about realism, explanation, and the nature of models become especially urgent in quantum physics, where the success of a theory rests on its predictive power and mathematical coherence, even as the ontological ground it claims to reveal becomes a matter of ongoing, robust debate. And in contemporary thought, discussions of information as a potential fundament, some modern proposals ask whether information or information processing could play a role as a more fundamental substrate than matter or energy, offer a further provocative way to interpret field theories. These ideas show how a turn toward information theory can illuminate questions about the nature of reality, about what it means for a system to have a state, and about how global properties of a system emerge from local interactions. In this longer arc, from Dalton's atoms to quantum fields, there are both the persistence of old questions and the emergence of new ones. The old question, what is matter, still matters, but it is refracted through new prisms. The old suspicion that there is a true, underlying substance that remains constant through transformations must now contend with the evidence that what we call mass, what we call charge, what we call inertia, and what we call a particle are not always fixed properties of a standalone thing. They depend upon interactions with fields, upon the geometry of spacetime, upon the context of measurement, and upon the collective behavior of many degrees of freedom. The new suspicion that the ground of reality might be relational, patterned, or informational offers a powerful synthesis of the empirical success of physics with a philosophical openness to novel metaphysical possibilities. Let us now turn to some cross-references that can deepen our understanding. In metaphysical discussions of substance, one often confronts the idea of whether a thing must possess an intrinsic essence or whether its identity can be defined by a network of relations and functions. In the matter and field story, we see a reconciliation of these strands. The material world is described in terms of fields, interactions, and patterns of energy. Yet the concept of substance persists in a different light, as a structural persistence of field configurations and symmetries. In the philosophy of science, debates about realism and explanation come into sharp relief as we see how a theory can provide reliable predictions without necessarily revealing a single, final essence of matter. The wave function, the field, And the vacuum energy, these are all elements that anchor disputes about what physics is telling us about the world and how best to interpret its formal structures. And in contemporary thought, where information is increasingly treated as a fundamental resource, one wonders whether the deepest architecture of matter might be described not just in terms of fields and particles, but in terms of informational structures that constrain and enable those fields to interact in the ways we can measure and manipulate. To anchor the discussion in concrete historical moments, we can read Planck's and Einstein's early struggles as the seeds of a quiet revolution. Planck confronted the ultraviolet catastrophe not by doubling down on a classical continuity, but by proposing a radical discontinuity in the emission and absorption of energy. He did not claim that matter was made of photons, but he did propose that the interaction between radiation and matter came in discrete packets of energy. The effect was to convert a problem about a spectrum into a problem about the possible states of a system. A shift from a purely dynamical view of matter to a view in which the fundamental processes of exchange and interaction become quantized. Then Einstein, by extending the quantum hypothesis to light itself, suggested a startling unity between what had been seen as two distinct realms, the wave-like, smoothed energy of classical electromagnetism and the particle-like behavior of discrete quanta. The two phenomena, photoelectric emission and Compton scattering, emerged from a single, unifying conceptual pivot, the reality of quanta. By the time Rutherford published his nuclear picture and Bohr offered spectral explanations, the atom had become a stage on which discrete processes could enact themselves within a relational framework. These episodes are not mere episodes in a laboratory notebook. They are milestones in a philosophical transformation about what matter is. If we pause to reflect on the quotes that have punctuated this journey, we can see how primary voices illuminate the path. Einstein's famous maxim, "God does not play dice with the universe," captures a tempering of quantum indeterminacy with a yearning for a more determinate order. But Feynman's wry reminder that I think I can safely say that nobody understands quantum mechanics punctures that longing with intellectual humility. The formal apparatus yields astonishing, precise predictions, but a single, tidy metaphysical story about the nature of reality remains elusive. Heisenberg's reminder that what we observe is not nature itself, but nature exposed to our method of questioning, pushes us to see that measurement, theory, and reality are bound in a manner that cannot be separated without losing essential content. These quotes do not settle the matter, but they illuminate the stakes of the debate. How much of what we call matter is what we can describe with a theory, and how much remains a question of what kind of thing the theory posits. The conversation about matter then becomes a dialogue about explanation, about what counts as a sufficient description of the world, and about how far our best theories can take us before we must revise our most basic assumptions. As we conclude this segment, let us keep in view the cross-disciplinary weave that makes the story of matter in physics so rich. The physicist's task is to produce models that match experimental outcomes with a remarkable degree of precision. The philosopher's task is to scrutinize the implications of those models. What do they reveal about the nature of reality, about the status of the objects they talk about, and about how we come to know anything about the world? Cross-references to metaphysical theories of substance and property help us see that the shift from a substance-based to a field-based ontology is not merely a technical detail. It is a reorientation about what counts as real and how reality is structured. Debates about realism, about how explanation should work, about the extent to which a theory describes reality versus merely organizes our observations, all pick up again in quantum theory and quantum field theory. And the possibility that information might serve as a foundational substrate, an idea that has gained traction in contemporary thought, offers a further link between physics and philosophy, inviting us to rethink causation, correlation, and the deep structure of physical law. Let us close with a final, integrating meditation. Matter in the physics we now practice and teach is not a stubborn, unchanging grain of stuff. It is a dynamic, relational, and highly structured range of phenomena whose most essential features appear through interactions, symmetries, and the fabric of spacetime itself. The journey from Dalton's atomic theory to quantum fields is not a mere chronicle of increasing sophistication. It is a philosophical drama about the nature of reality, the limits of human knowledge, and the kinds of entities that physicists can meaningfully claim exist. We should be grateful for the clarity that experimental results provide, and we should also honor the complexity of interpretation that these results demand. The matter we seek to understand is not a final fossil left behind in the mind of nature. It is a living, evolving concept that has grown and changed with our best theories and experiments. In this sense, the matter of physics is an ongoing dialogue, a conversation between the world as it is in itself and the human mind that strives to understand it, a conversation that continually reallocates the terms of what counts as substance, what counts as property, and what counts as a real explanation. This exploration of matter in physics, from atoms to quantum fields, offers more than a historical tour. It is an invitation to reflect on how scientific theories reshape our philosophical conceptions, and how philosophical questions, in turn, reinvigorate scientific inquiry. If you found yourself surprised by the ability of a field to endow particles with mass, or by the way a single Higgs field can influence a spectrum of particles, you are not alone. These insights are not anomalies that disrupt common sense. They are the natural outgrowth of a history in which nature, theory, and language co-evolve. They remind us that there is no final, settled moment in our understanding of matter, only a continuing process of reinterpretation in light of new evidence. A process that keeps guiding us toward deeper questions about the ultimate ground of being, about what it means to say something is real, and about how best to tell the truth about the world through the language of physics. As you watch the rest of this video, you will hear more about how these ideas connect to discussions in other parts of the curriculum, how metaphysical theories handle the notion of substance versus process, how the philosophy of science debates realism and explanation, and how contemporary discussions about information as a potential fundament provide new ways to think about what matter is. We will juxtapose more examples, including the uncanny phenomena of quantum tunneling and the coherence in superconductors. And we will revisit Planck's seed of quantization and Einstein's photoelectric demonstration as moments where the human mind glimpsed the possibility that the ground of physical reality is more subtle than our everyday intuitions. If you take away one thing, let it be this: matter is not a single unchanging core that simply sits beneath the world. It is a living network of fields, interactions, and structures that come alive in the acts of measurement, interaction, and observation. The history of physics is a history of our going deeper into what counts as real, and of learning to recognize the way that reality discloses itself through the elegant mathematics and stubborn experiments that scientists carry forward in each generation. What is matter, really? When we step back from the word and listen for the texture beneath it, matter is not merely the stuff around us, the rocks and metals and plastics stacked in shelves and warehouses. Matter is the ground of experience, the stubborn soil through which perception presses, the stubborn medium by which touch, sight, and sound become meaningful. In this segment, we will travel through origins, arguments, and practices that braid together embodiment, ecology, and aesthetics, asking how matter appears in lived experience, in technology, in culture, and in the vaster networks that connect them. We will move from the intimate sensation of touch to the planetary scale of resource flows, from ancient clay to 3D printed prosthetics, from the ritual of clay and stone in a temple or a square to the digital matter of data that travels as bits through a global nervous system. We will ask not only what matter is, but how matter insists on being seen, used, or respected in a world that is at once intimate and enormous. Let us begin with origins, where philosopher and artist alike often sense a hinge between the primitive sense that matter is something you can touch and the more delicate sense that matter is a social and political actor. For thousands of years, thinkers have asked what material substrate makes possible the forms we inhabit. In the pre-Socratic wake, there was a sense that the world can be traced back to a fundamental stuff: water, air, fire, earth, or some primal principle that organizes itself into the bodies we know. Thales, the earliest of the Greek natural philosophers, is famous for declaring, in a concise, blunt claim that future generations would debate and echo, that all is water, all is water. In that short line, we glimpse a position that will haunt Western thought for many ages. Matter is not merely inert, it is active, dynamic, transformative, and capable of taking on forms that surprise us. If water shapes not only rivers but the bank of a shore and the grain of a blade of grass under the sun, then matter is not simply passive substrate, it is a force that organizes the world. And Heraclitus, who would remind us that you cannot step into the same river twice, makes the claim with a different emphasis: flux, the world, he suggests, is always becoming other than what it was only an instant ago, and matter is braided with time in a way that makes stability itself a kind of illusion. The river is not simply water, the river is event, process, a becoming whose border dissolves as you reach for it. In these ancient reflections, we encounter a question that still runs beneath our modern debates. Is matter a fixed substrate, a stubborn thing that can be weighed and measured and catalogued, Or is it a process that reveals itself only when we attend to the way things resist, invite, and rearrange our attention? From that ancient threshold, we move to a more modern vocabulary that centers the lived body as the site where matter becomes meaningful. Husserl, beginning from the primacy of consciousness, insists that phenomena must be examined as they present themselves to us in intentional acts. But phenomenology, as Merleau-Ponty develops it, insists something more radical. The body is not simply a thing among things. The body is the primary inroad to the world. Our senses, our grip, our posture, our tremor, even our fatigue, that is where matter first appears as matter to us. When we perceive a surface, a material texture, or a weight in the hand, we are not merely reconciling with passive data. We are engaged in a conversation with the material world that is mediated by our living, breathing presence. For Merleau-Ponty, the body is not an instrument we wield, it is the field in which the world discloses itself. This is a crucial pivot. Matter is not only external stuff, matter becomes meaningful through embodiment. The texture of clay in a potter's hands, the weight of metal on a forge hammer, the resistance of a leather belt in a loom, these are not mere properties, they are the conditions of sense. This line of thought points toward what we might call the phenomenology of matter. If embodiment allows matter to disclose itself, it follows that to think matter is to think through how the body is shaped by it and how the world is shaped by us in response. Husserl's idea of the world as given in perception, when translated into this embodied register, becomes a claim. Matter is given to us in a field of felt possibilities, in a texture of possibilities for action, for use. For care, Merleau-Ponty's insistence on the body's primacy reframes the material world as something we are always in the middle of, never merely observing from a distance. The chair you sit on, the screen you touch, the air you breathe, each is a boundary and a bridge between you and something else, a moment in which matter and meaning co-emerge into this living, sensing world. Step the mediating technologies in the late 20th century turn toward post-phenomenology. Don I, with his emphasis on mediations, invites us to attend to how instruments become the disappearances and revelations of the world. A microscope, a telescope, a camera, a computer, each is not simply a tool we use to extract information, each is a way of constituting reality. The device becomes part of the world we inhabit, shaping what we see, what counts as evidence, and what counts as real. Technological mediation thus reframes the question of matter. Is matter simply what remains after our tools do their work, or is matter distributed across networks of artifacts, laboratories, and practices that themselves demand our attention? Its post-phenomenology pushes us to recognize that the material world is not a uniform field of stuff, but an ecology of relations in which tools, bodies, and environments co-develop. Heidegger adds a daring, sometimes unsettling, dimension to this discussion through his analysis of tool being and the handling of equipment. The ready-to-hand tool is most revealing when it disappears into use, in the smooth competence of a craftsman turning a chisel, the tools being as legible in its usefulness, the wooden handle, the metal blade, the way light glints off a polished surface, all communicate a sense that the material world is ready to reveal itself as a field of possibilities for action. When a tool breaks, it becomes present at hand. The world is disclosed not through use, but through the disruption of use. In that moment, the world no longer offers itself as a network of projects, but as a field of obstacles. This is not mere technical trivia. It is a philosophy of matter that insists material readiness, how materials are prepared, presented, and prepared to be used constitutes a crucial aspect of our relation to the world. If we keep moving with these thinkers, we arrive at a more contemporary turn that rethinks matter as something with agency in social life. Lador, a central figure in the actor network approach, argues that actants, humans, technologies, institutions, texts, even natural elements, are all actors within networks that produce what we call reality. In this sense, matter is not inert substrate, but a force within networks that helps to stabilize some relations while destabilizing others. The cable that carries electricity, the mineral ore transformed into computer chip, the policy document that channels funding towards sustainable construction, each of these is a link in a network where matter has a form of agency. Lador's project invites us to trace the social not as a mere human set of practices, but as a web in which matter participates and influences outcomes. The concept of networks helps us understand why a single choice about material sourcing can ripple through climate policy, labor conditions, and even global cultural tastes. Cultural theorists, too, have pushed the matter question into the public sphere. The field of material culture studies asks what our daily objects tell us about social values, identities, and power relations. Objects are not neutral, they participate in political life. The design choices that shape what is produced and how it is consumed encode norms, biases, and aspirations. To study material culture is to follow the traces of meaning that pass through brick, plastic, and glass, and to see how those traces influence who we are and how we live together. This is not mere aesthetics, it is ethics in the sense that to decide how to use a material, to choose what to design, to place a sculpture, or to construct a building is to commit to a particular care for the world. And if we turn toward eco-philosophical perspectives, matter becomes a matter of responsibility. Bruno Latour's environmental critiques and eco-philosophers remind us that material choices are not private preferences but public consequences. The concept of actants and networks helps us see how energy flows. Minerals are extracted and ecosystems are affected by the design of technologies and the structure of economies. The politics of materials, the ways we mine, refine, transport, and dispose of matter becomes a central question for ethics. The call is not only to reduce harm, but to reimagine production and consumption in ways that respect the life of soils, waters, and atmospheres. In this sense, matter is not a spectacle of mastery, but a field of responsibility. If we ask how the material turn manifests in the arts and design, we find a vibrant, hands-on domain where matter no longer plays a passive supporting role. The material turn in art asks, how does matter speak through form? How does the texture of soil, the patina of stone, the grain of wood, or the granularity of metal reveal something about place, history, and politics? Sculpture is a long-standing arena for this inquiry. A block of marble becomes a subject, a memory, a political moment in which the ancient craft and contemporary concerns collide. The terracotta sea of a coastline, the mud and pigment smeared on a mural, the glass that refracts light in a gallery, these works insist that matter has presence, even voice. In design, matter is not a backdrop but the main stage. Material choices, biodegradable plastics, recycled composites, the use of local resources become ethical statements. A chair designed from a local timber stock and set with a finish that can be recycled speaks to a culture's respect for place, history, and care for future generations. This is where the digital age complicates the matter picture in provocative ways. Digital matter and data occupy a paradoxical space. They are immaterial in their immediate feel, bits and bytes that float on screens and servers, yet they have a physical substrate and a real energy cost, the silicon wafer. The copper wire the data centers ping in a moment of communication. These are forms of matter that operate across distance, time, and scale. Data is not phantom, it is material in a hard, undeniable sense. It resides on femtoscale circuits, it consumes energy, it radiates heat, and it is subject to physical loss and piracy. The question then arises, can information be considered a form of matter? A kind of matter that exists in a different register but remains real as a matter of physics? And if so, what does that imply about responsibility? If your personal data, a corporate data trove, or a weather dataset has real, measurable effects on people, ecosystems, and economies, then data moves from being a metaphor for knowledge to a material agent with consequences. This is the moral weight of digital matter, choices about data storage. Processing and sharing are decisions about energy use, privacy, autonomy, and ecological impact. To illuminate the ethical terrain, we can look toward design ethics and environmental philosophy. The cradle-to-cradle concept, advanced by designers and scholars, calls for products that are endlessly repurposable, materials that can cycle through cycles of use, reuse, disassembly, and return to the earth with minimal harm. This is not merely a technical challenge, it is a philosophical stance. Matter should be treated as a cooperative partner rather than a disposable resource. The moral imperative is clear. The material choices we make in manufacturing, packaging, and consumer culture contribute to climate change, to pollution, and to the unequal distribution of environmental burdens. Design that accounts for end of life, that favors renewables, that minimizes toxic substances, and that respects local ecologies embodies a kind of material ethics. It asks of every object, what is your life cycle? Who bears the costs of your existence? Who benefits from your existence? And how can we reimagine your very possibility so that future beings inherit not a polluted archive but a living, capable world? The cosmopolitan reach of matter becomes clearer when we cross cultural boundaries and ask how different traditions conceive matter through practice and ritual. In many indigenous and ancient cultures, matter is not simply inert or inertially meaningful. It can be animated, sacred, and relational. The earth, the stone, the plant, the mineral, the animal, all are beings withstanding in a web of reciprocity, the matter of a sacred ceremony. The pigment used in a body painting, the clay a potter shapes with a lineage of kin in every seam. These are not just materials used, they are participants in a shared life. in East Asian thought. The idea of chi or prana gestures toward matter as a field of life energy, a substratum of vitality that binds bodies and surroundings. In many African and oceanic traditions, objects carry memory and agency. Their manufacture, repair, and use are communal acts that sustain social bonds and ecological balance. In these worlds, matter is not a passive substrate awaiting human mastery. It is a collaborator with cultures that have learned to live with soils, waters, and climates in ways that emphasize maintenance, reciprocity, and care. The material world also shapes medicine, industry, and environment in concrete ways, revealing the intimate alliance between material science and lived life. In medicine, materials, biopolymers, implants, prosthetics, hydrogels, and biomaterials become not only tools but participants in healing. A biocompatible scaffold, a 3D printed prosthetic limb, a biomaterial that supports tissue regeneration. These are feats of material science that reconfigure what is possible for patients. The body becomes a site where material limits and clinical innovations meet, a place where a patient's everyday life is reimagined by new forms of matter. In industry, materials enable scales of production and new forms of mobility, composites that cut weight yet increase strength, metamaterials that manipulate waves for better sensors, and nanoscale materials that alter drug delivery. In ecology, the life cycle of materials, extraction, refinement, use, reuse, and disposal exposes the deep connection between human economies and non-human ecologies. The planetary scale of material extraction reveals the ethical stakes of resource use, recycling, and sustainable design, and yet we must keep a watchful eye on counterarguments. Some critics fear that this materialist or post-material turn risks reducing culture to mere stuff. They protest that to dwell on matter too long is to risk ignoring the meanings, values, and symbols that cultures produce through sign, ritual, and language. They worry about what they call immaterial labor, the ways in which cognition, culture, and social life are generated through intangible activities like design thinking, software development, and cultural production. They remind us that experience often transcends material constraints and that human creativity frequently moves beyond what the most careful analysis of materials would predict. If we become enthralled by the agency of matter in circuits and soil, we may neglect the ways in which human life can transform even the least material thing by intention, care, and imagination. The critique warns against seeing matter as the sole protagonist in the drama of existence, leaving human agency and interpretive life in the wings. A second counterargument emerges from the horizon of horizons rather than substrates. Some philosophers have urged that matter itself may be a horizon beyond which our concepts fail to traverse, a boundary that resists ultimate reduction to physical properties or measurable effects. In this view, matter is not simply a rational inventory of atoms, energies, and cycles, but a horizon of possibility that recasts how we imagine reality. The insistence here is not that matter is unreal or only a social construction, but that matter is not exhausted by our present theories. There are dimensions, ethical, aesthetic, phenomenological, that resist complete codification. A world of material presence can still be an invitation to wonder, mystery, and reverence. This is a reminder that even within robust scientific theories, there are margins of experience that resist totalization, and those margins matter for how we live. To see how all this plays out in the lived world, we can hinge a few concrete examples that anchor the discussion. Consider 3D printing and prosthetics. A patient born with an abnormal limb or a veteran losing a limb in conflict can now receive a prosthetic tailored with astonishing precision to the wearer's anatomy. The material choice, flexible polymers, lightweight titanium alloys, bio-inspired textures, matters for comfort, control, and selfhood. The prosthetic is not merely a device, it is a material extension of the body, a partner in daily practice that reshapes what is possible. From gripping a cup to running a race, the material limits are redefined. Shapes can be produced that would have been impossible with traditional manufacturing. The question becomes, how does the patient experience the prosthetic as material presence rather than mere tool? And how do designers and engineers attend to the embodied knowledge of users to produce devices that fit into a life? Biodegradable plastics and waste cycles provide another luminous case. A world anxious about plastic pollution presses designers and policymakers to consider materials that do not leave long-lived traces in earth and water. This is not simply a technical constraint, it is a matter of ethics, aesthetics, and ecology. The material becomes a site of political negotiation. Farmers and factories, scientists and citizens, communities and regulators all weigh in on what constitutes responsible material stewardship. The shift toward compostable or recyclable materials is a cultural act that redefines what counts as value. It invites designers to consider product life cycles, to imagine reuse and rebirth rather than end-of-life disposal, and to conceive of materials as partners in planetary health rather than as disposable commodities. Art installations that use soil, clay, or stone to evoke material presence remind us of the sensuous dimension of matter. When an artist arranges soil into a landscape within a gallery or uses clay to evoke memory and place, the audience experiences matter as a presence rather than as inert. The material here becomes a pedagogy about time. Clay dries, cracks, reverberates with the breath of viewers, and invites touch, debate. And memory, the act of working with earth, reveals both the potential and fragility of material worlds. A visitor who kneels and feels the cool clay becomes part of a larger conversation about place, labor, and the relationship between the human and the earth. Digital fabrication and virtual reality present another frontier. Digital matter, data, algorithms. Simulations promises a new form of materiality that is not visible at first glance but is felt through its consequences. A design produced by digital fabrication is only realized when the machine acts upon a digital plan to produce a tangible form. The process reveals a paradox. The plan that guides the hand exists in an abstract space, yet its consequences are material, physical, and measurable. Virtual reality can make the boundary between digital and material vanish in important ways, as immersive experiences can persuade, educate, and transform attitudes about the world. The question is how to preserve a sense of material accountability within a space where the boundary between simulation and reality can blur. If we draw the threads together, we arrive at two revealing lines of argument that cross the history of thought and the texture of daily life. First, the conflict between reductionist materialism and anti-reductionist accounts of lived experience continues to shape debates about what matters in the world. A reductionist might insist that everything, ultimately, reduces to atoms in motion and that all cultural meaning is a byproduct of brain activity or emergent properties of complex systems. An anti-reductionist would insist that there are irreducible dimensions of life, value, intention, ritual, aesthetics, care that cannot be captured by a map of particles and forces alone. The material world, in this view, has depths that resist complete codification. The second line comes from the recognized reality of digital matter. Data and information are not immaterial, they are physical, they have energy costs, and they shape economic, political, and ecological outcomes. The material status of information demands a rethinking of responsibility. How we store, transmit, and delete data matters, because what we do with information leaves traces in energy use, privacy, and social organization. To those who worry that matter erases culture, let us remember a basic anecdote from the history of sculpture. The transformation of clay into bricks that became walls, or the transformation of marble into columns that hold up a temple or a statue that communicates a cultural memory, is a story about matter shaping meaning. In ancient sculpture, clay and marble were not mere subjects, they were agents that absorbed the hands, the tools, the earth, and the sky into forms that could speak across centuries. The same material, shaped by a craftsman's vision or a workshop's plan, could convey a memory of a city, a religious event, or a social ideal. A culture's values are inscribed in the material choices it makes, in the ways it manipulates, preserves, and recycles matter. The Renaissance, with its mechanical arts and the rise of a material culture studies discipline, is a landmark in the shift from matter as mere substrate to matter as a dynamic field that participates in human knowledge and power. When painters and sculptors learned to see stone and pigment as active partners in expression, they invited a shift toward material awareness in a way that still informs contemporary design. This history also offers a first historical anecdote, the transformation of clay and marble in ancient sculpture. Think of a statue emerging from a raw block. First only a rough concept of a figure, then an indistinct mass, and finally the Chinese letter finish that reveals light and shadow, grain and tone in the living space of a temple or agora. The material speaks through the artisan's hands, the surface becomes a language of memory. The ancient world did not separate matter from meaning in the way later science sometimes does. Matter in that tradition was a partner in the production of beauty, a partner in ritual and a witness to human aspiration. The gaze that contemplates a statue is not a mere gaze at a thing. It is a moment of encounter with a field of matter that has been cultivated, shaped, and called into presence by human intention. A second historical anecdote moves forward to the Renaissance and the mechanical arts. The Renaissance marks a turning point in which material culture becomes a central site of inquiry, experimentation, and self-understanding. The revival of classical sculpture sits alongside a new confidence in technique, proportion, and the capacity of materials to carry new meaning. The mechanical arts, metalworking, painting, architecture become fields where matter is tested, measured, optimized, and transformed into instruments for new kinds of knowledge and power. The materials themselves, the metal alloys, the pigments, the stone are not simply passive. They enable experiments with perspective, with optics, with engineering. The emergence of an expanding material culture, the sense that matter could be engineered toward specific ends, foreshadows the later, more explicit exploration of materiality in the philosophy of technology and in contemporary design. It reveals how the appropriation of matter for shared ends, beauty, utility. Knowledge has long been a central impulse of human culture. If we carry this sense into modern times, we find ourselves in the era of planetary-scale material extraction. The scale of mining and resource use cannot be separated from questions of climate, habitat, and the rights of communities near extraction sites. The environmental and social consequences of material throughput compel a philosophical inquiry into responsibility, justice, and sustainability. The idea of a supply chain is not simply economic jargon. It is a chain of ethical obligations that links a mine in one country to a factory in another, to a consumer's daily habit, to a politician's policy. The material world becomes a site of political contest about who benefits, who pays the costs, and how to distribute the burdens of resource use justly. A philosopher of matter must attend to this scale. Because the fate of rivers and forests, the health of communities, and the future of species depend on the decisions made in design rooms, on the factory floor, and in the boardrooms that decide which materials will be mined, refined, and sold. In this context, the idea that matter is a horizon rather than a fixed substrate begins to return with renewed force. If matter is a horizon, then the projects we pursue, whether for medicine, energy, or culture, redefine what we can hope to know and become. The horizon is not empty. It is the limit that invites us to step beyond. It invites us to imagine materials not as passive things, but as partners in a forward-looking project that blends science, ethics, aesthetics, and care. The horizon moves as we move. The future of matter is not a predetermined destiny. It is the consequence of the ways we choose to engage with the world, the resources we honor, the technologies we create, and the communities we nurture. To ground these reflections with explicit cross-references, we can trace lines of dialogue across disciplines. In environmental ethics, the question is what we owe the more than human world when we mine, refine, and consume matter. The climate crisis presses for a robust, action-guiding ethics that recognizes material choices as moral choices. In the philosophy of technology, the notion of tool being and post-phenomenology invites us to look at how technologies reconfigure human embodiment and perception, shaping what we can do and what we come to value. In aesthetics, the material turn prompts us to see art not merely as a display of form, but as a negotiation with matter that engages the senses, memory, and place. In cross-cultural philosophy, the diverse conceptions of matter as animate, relational, energy-infused, or sacred compel us to move beyond one-size-fits-all theories and toward a plural philosophy of matter that respects different traditions and practices. Let us close by returning to a few guiding images and a few guiding questions that can anchor your own inquiry. First, imagine a clay pot being formed on a wheel. The clay is alive with the fingerprints of the maker, the wheel's revolution, the moisture that makes it malleable, the heat that will later set its form. It is not merely material, it is event, history, and intention. It embodies both the intimate acts of care and the social world that will use, appreciate, and reuse it. Second, picture a data center tucked away in a landscape of batteries and metal racks. Humming with energy and light, the data inside does not vanish when you close your laptop. It persists somewhere, wherever the server breathes, where power is drawn, where networks ferry signals across continents. It is a reminder that even the most seemingly ethereal forms have physical roots and consequences. Third, consider the soil within a sculpture garden. The texture of tireless earth in a gallery space, the way a viewer's fingers brush dust and air as the sculpture seems to emerge from soil and memory. These images invite you to think of matter as a living spectrum: earth, metal, plastic, data, energy, each a conduit of life, culture, and care. In the spirit of cross-references, we can weave a map of this inquiry across several terrains. To environmental ethics, we bring a shared concern with minimal harm and equitable stewardship of the planet's resources. To the philosophy of technology, we bring a focus on mediation, embodiment, and the co-creation of reality through artifacts and systems. To aesthetics, we bring a sense that art helps us feel matter as presence and process, not just as substance. to cross-cultural philosophy. We bring the knowledge that traditions vary in how they experience matter, what matters, how it matters, and to whom it matters, inviting humility and pluralism in our theories. And to philosophy of science, we bring a recognition that the material world is not a neutral backdrop to inquiry, but a dynamic participant in the unfolding of knowledge, limitations, and possibilities. In closing, two small but persistent lines from ancient and modern voices can accompany us as we continue this inquiry. From Heraclitus, we have the reminder that you cannot step into the same river twice. Material worlds flow with time. Our encounter with matter always occurs within a present that contains the past and the future. From the modern turn, Ladder's insistence that we must trace the life of networks reminds us that matter is not a solitary actor, but part of a web of relations that includes people, circuits, policies, and beliefs. The river and the network together teach us that matter is neither simply substance nor simply symbol. It is a medium of life and a field of responsibility, a partner in culture, and a patient witness to our choices. If we attend to matter in this way, with care for embodiment, for ecology, and for aesthetics, we may find a more delicate, honest way to inhabit the lived world. We may learn to see matter not as an obstacle to overcome or a resource to hoard, but as a companion in a shared life, a life bound to soil, to circuits, to voices, to futures yet unmade in this longer arc of thought. The task remains to keep the conversation open. How can we continue to map the landscapes of matter without losing sight of the human stakes? How can we balance the enchantment and fear that matter awakens in us, its beauty, its violence, its dependence on care? How can we tell stories about matter that join the sensuous, the ethical, and the political? These are not questions with easy answers, but in asking them, we keep alive a tradition that treats matter as a living interlocutor in the drama of existence. The lived world is not a stage on which mere forces act. It is a shared field where humans and non-humans, materials, technologies, ecosystems, and cultures become together in a multi-species, multi-centered conversation about what it means to live well. And as we listen to this conversation, we discover that matter is never simply there. It is here with us, in our hands and in our futures, asking us to choose how to care for what sustains us and what we might someday become.